Morning.
Morning. Okay, so we are live.
Viviana, podemos começar então?
Sim, estava só a fazer um compasso de espera para ver se as duas outras participantes da manhã apareciam, mas
A
vamos
Franciane
começar
está
com
ali.
Hi, I'm here.
Só que está
Oh,
indicado
okay.
João.
Sorry. Your name is João on your screen, so I didn't know it was you. I'm so sorry.
Ai, desculpa, é que eu estou no notebook do meu marido.
Não há problema nenhum. Pronto, então vamos começar. Let's get started then. Good morning. So I just received here a message from Ricardo Ramalho, who wishes to say that yesterday about the submarine cables on Rashid's intervention on tsunamis. He says it's Luís Matias who is involved in submarine cables and not Susana Custodio, so just for the record. And now I will shortly share my screen just to so that we can take a quick look at today's schedule. So for the first hour, we have three talks by new researchers, first with Elisa Sanchez, then with Elizabeth Mullify, and then Franciane Santos. Next, we have another hour of new PhD students' presentations, pretty much like yesterday. Then we will have our very sad virtual coffee break. And then two special interventions. The first one is to attribute the IDL awards for best PhD of 2020. And then we will finish the annual conference with the invited talk by Michael Way from Goddard Institute for Space Studies. Here's the title, just as a quick reminder. And now I will, unlike yesterday, I will stop sharing my screen and I will give the floor to Elisa. Since yesterday we had some not so agreeable difficulties from participants, I think today, for at least for the first session, only 3 people, I think will you can safely share the screen with them. So Elisa, whenever you're ready.
Good morning, everyone. My name is Elisa, and I joined the IDL last summer with a fellowship from Fundação de Ciencia y Tecnología. I studied geology in Zaragoza, Spain, and I did my PhD in Burgos, Spain, about paleo-magnetism and paleo-intensity over Pliocene lava flows from Lesser Caucasus. In this talk, I'm going to present my project to be developed at the IDL, which I do in collaboration with Eric Font, also associated with IDL and Universidad de Coimbra. First, to start, I will give some basic points about palomagnetism. There are different mechanisms by which rock acquires natural remanent magnetization. In case of sedimentary rocks, it is a mechanical process called detrital remanent magnetization. When a sedimentary rock is formed through the deposit of detrital grains in calm water, the small ferromagnetic grains, previously magnetized, had freedom of movement during their fall, and the Earth's magnetic field orients these particles in their direction. Then they are incorporated to the sediment with a preferential orientation parallel to the Earth's magnetic field. When dehydration and lithification of the sediment occurs, the position of the grains is finally blocked and also their magnetization. Given the nature of this mechanism, assuming a constant sedimentation rate, we get high resolution and continuous record over time. This type of records can suffer from the positional effects like diagenesis, compaction, or diaturbation. As we all know, the magnetic field on the Earth's surface is a vector with declination, inclination, and intensity, different depending on the position in the globe where we are. Therefore, from rocks that record a natural remanent magnetization generated by the Earth's magnetic field at the time of the formation, we can obtain the magnitude of declination-inclination of the Earth's magnetic field and intensity of magnetization proportional to the Earth's magnetic field. The palomagnetic vector recorded in rock can be measured thanks to very sensitive magnetometers used in palomagnetism laboratories. In my case, I work with the spinner magnetometer of the IDL laboratory, and also I collaborate with the laboratory of Burgos, where there is a superconducting magnetometer. Once we have understood the basis of palomagnetism, I will go to the specific characteristics in speleothems. How speleothems acquire the natural remanent magnetization? By magnetic minerals that infiltrate from the soils capping the cave, like magnetite or hematite, among others. Magnetic minerals from deep water are aligned with the Earth's magnetic field when they are deposited in calcite layer. Given the acquisition mechanism and almost continuous deposit and the lack of post-depositional effects, speleothems are an excellent high-resolution Earth magnetic field record. The type of geomagnetic record that we can obtain from speleothems corresponds to the Earth's magnetic field variations. One of these variations is the secular variation. It is a constant movement during which it can be observed how the north magnetic pole moves around the north geographic pole. This is an example of paleosecular variation record on a speleothem from China, where the geomagnetic declination and inclination is obtained for the last 9,000 years. This is another record of declination, inclination, and also relative intensity in a speleothem from Algarve, obtained by Jorge Ponte during his thesis here at the IDL. Another type of variation of the Earth magnetic field that can be recorded by speleothems are geomagnetic excursions. They are a punctual destabilization of the field as polarity reversals, but that are not result in a change of magnetic polarity. A negative pole becomes north again. This is an example of the Blake excursion recorded in a speleothem from Cantabria, and we can see the declination here and inclination variation. Here, the latitude variation of the geomagnetic pole is represented during several excursions recorded in a flowstone from Italy. After this background, I'm going to present the main objectives of my project and some preliminary results. The objective of my project is obtain high resolution record of the Earth magnetic field behavior. And the main motivations are that speleothems can provide high resolution and mostly continuous records. They can be dated by radiometric methods. They are not affected by depositional effects. And Portugal has a rich but still untapped heritage of cave system and speleothems. First, I have worked with a stalagmite sample in Soprador do Carvalho cave in 2019 by Luca Di Muccio from Department of Geography of Universidad de Coimbra and Eric Font. 45 plates of 6 millimeters were extracted with which the palomagnetism experiments had carried. For uranium thorium etches made by our colleagues in Canada are available for the stalagmite. With these 4 etches, I made an edge model using a software that interpolates edges and the depth of different samples. Finally, a stable magnetization has been obtained for most of the samples that has allowed the construction of declination, inclination, and relative intensity curves. To finish, in September, we made a new campaign in the cave of Lumiar dos Morcegos, near Albado, in the Macizo Calcáreo Extremeño. We collected 3 new stalagmites, and now we are cutting and preparing the samples for the next experiment. And this is all, and obrigada pela sua atenção.
Thank you, Elisa, for your presentation. Any questions?
May I?
Yeah, go ahead, Ricardo.
Hello, Elisa. Thank you. Very good presentation. I just would like to ask you, so what sort of signals, let's say, you're expecting, let's say, to find, or what sort of lessons are you think you would like to find with this approach?
First, get more data for the paleosecular curve for Iberia, no, Peninsula Iberica. But would be great to find a excursion.
Okay.
Or maybe something like a jerk is a fast movement into the paleosecular variation or something like that. We will see.
Okay. Thanks.
Thank you. Any more questions?
Hi, Elisa. I was wondering if this type of climatic reconstruction can be merged with other type of climatic reconstruction from sediments in lakes. I've been cooperating with people doing some sediment cores in lakes in Serra da Estrela, and with Spanish colleagues also reconstructing for the last 2000, or even now in Serra da Estrela for the entire Holocene. So you think it's possible to merge some of these in terms of hydrological cycle relevant variables?
Could you repeat the last one?
In terms of precipitation or variables that are relevant, not only temperature, but also related with the hydrological cycle.
Yes, no, the little minerals in the speleothems depends of the precipitation, no? The rain and another climate process, and if in the same time could be correlated with the lakes, I think.
Okay. What type of temporal resolution you have with your
the HE models, or
no the minimum time slice you have?
Okay, time slice. In the first stalagmite we take 6 millimeter plates, as maybe is 6 or 6 layers, no, of calcite.
Okay.
But now for the next stalagmite we will go to sampling small cylindrical samples for take only 3 or 4 layers, calcite layers, and then the resolution will be better.
Okay. Thank you.
So Elisa, just a quick question. Sorry, if I may.
Yeah, go ahead.
So that means you'll have in age intervals, or roughly the time interval of your resolution is what, 10 year scale or longer? Smaller? Is each layer in the stalagmite corresponds to a year?
I don't know. Its layer is stational, no? Maybe it's black and white is 1 year, no? Eric, could you reply?
Yeah, we can assume that each layer is almost annual.
1 year, or
Yeah.
maybe 2 layers, no? Black and white 1 year, because maybe it's stational.
Yeah, normally
Okay.
there are tendencies of black and of detrital, darker and bright laminas is probably seasonal. So we can assume something that is annual. The problem, as Ricardo said, is it would be very interesting if we can go to spectral analysis or something like that of on the scale of the years. But we have a problem, which is the sampling, because it's so thin. Then, for example, if you have a 1 millimeter thick saw, if you cut it, so just cut it, and you lost 1 or 2 years by cutting it, because it's extremely thin. But yes, we can assume that the laminas are annual, and if we are able to study them at millimeter scales, we can have annual records. But in practice, it's not easy. So if we have 0.5 centimeters scale sample, it's almost 5 years. So the minimum time scale is 5 years, 10 years per sample.
It's still very good. So
yeah, it's still very good. It's much better than any other geological records. And you have not the problem associated to the lakes, for example, the lakes that Ricardo mentioned. You can have several problems, geogenesis, bioturbation, compaction, etc., that you don't have in speleothem. So this is why they are quite good for climate and geophysical records. Yeah.
Sure. Thank you.
Maybe we should be getting on with our schedule. I don't know if anyone has any more comments. Then I will carry on with Elizabeth Mullify. So Elizabeth, go ahead and share your screen, okay? You have to turn on your microphone.
Okay. Hello, good morning.
Hello.
I'm trying. Wait, sorry. Okay. Are you seeing my screen? Yeah? Okay. So, good morning. My name is Elizabeth Mullify. I finished my PhD in 2017 in geology with specialty in paleontology and stratigraphy. And during my PhD, I studied the fossil record of theropod dinosaurs from the Upper Jurassic of Portugal. And I started recently a contract as junior researcher at IDL with a project that aims to study the changes in the faunal composition of Iberian theropods through the Jurassic and Cretaceous. So this presentation is mainly some of the results achieved during my PhD project. And I'm going to show you also some of the work that we are doing more recently. I'm sorry, I think I open this problem. I'm sorry. This project aims to understand the Mesozoic ecosystems with continental vertebrates from the Iberian Peninsula. There are several other colleagues that are working in this project with other fossil records. And besides, to understand the evolutionary history of these vertebrates, we are also trying to understand the paleo-environmental context of this fauna based on sedimentological and stratigraphic analysis, as well as on the study of other fossil records, mainly paleobotanical and microfossils. Other important goal of this project is to understand the paleobiogeographic relationship of the Iberian vertebrates, particularly with correlative faunas from North America, in order to understand the evolutionary history of this fauna in the context of the opening of the North Atlantic Ocean. So the main objective of this project is to characterize the faunal composition through the late Jurassic and Cretaceous and understand the drivers of the faunal turnover that occur during the Jurassic Cretaceous transition. So first of all, a brief introduction to the theropods. So theropods were a group of mostly carnivorous dinosaurs known in the fossil record since the late Triassic, and that includes the lineage that gave rise to birds. So it is the only group of dinosaurs that survived the mass extinction at the end of Cretaceous and that has representatives nowadays. This group includes giant forms, such as the famous tyrannosaurs that could reach more than 12 meters in length, but others were relatively small with only a few centimeters. This is a small avian theropod, Archaeopteryx, from the Upper Jurassic of Germany. This is one of the oldest known birds, and this specimen has a combination of features shared with primitive theropods, such as the presence of teeth or a long bony tail, together with features typical of birds, including the presence of fly feathers. This specimen was the first evidence of the transition between primitive theropods and birds. So it was very significant to understand the origin of birds. The fossil record of Portugal is very rich in vertebrates, particularly dinosaurs. Most of these fossil records came from the sedimentary units that form the Lusitanian Basin, which is a sedimentary basin originated during the late Triassic, and which origin is related with the opening of the North Atlantic Ocean. And so it is in these mainly Upper Jurassic sediments that form the infilling of the Lusitanian Basin that we have been finding most of the dinosaur fossils known in Portugal. The majority of the fossil sites are located in the coastal region of the central sector of the Lusitanian Basin. However, there are some very important fossil sites in more northern and inland areas. This higher incidence of findings in the coastal region is at least in part related with the more extensive outcrops available, which on the other hand are constantly exposed to coastal erosion, so incrementing new findings and facilitating the prospecting works. On the contrary, in more inland areas, the outcrops available are very reduced, and the paleontological findings are usually associated with some kind of construction works. The dinosaur fauna from the late Jurassic of the Lusitanian Basin has been traditionally interpreted as closely related with correlative levels of the North American Morrison Formation and the Tendaguru Formation in Tanzania. Particularly, the discovery of this theropod specimen in a locality near Pombal, which was assigned to Allosaurus fragilis, one of the theropod species more abundant in the Morrison Formation. And this specimen was interpreted as the first dinosaur species with the intercontinental distribution, and thus promoted an intense debate about the possible existence of faunal interchanges across the Proto-North Atlantic during the Upper Jurassic. However, in the last years, there are identified some exclusive forms for the Lusitanian Basin and other that seems related with other geographic areas. So it indicates a more complex paleogeographic scenario, which is not yet well understood. So to try to understand this, we study the abundant fossil record of Portugal. Here we have some specimens of theropods from this record. These dinosaurs are mostly represented by isolated materials. However, there are also some articulated or associated specimens, including some fairly complete skulls, such as this beautiful specimen here that belongs to the collection of paleontology of the Museu de Lourinhã. And during my PhD, we study several collections with theropod materials. This is part of a private collection that includes dozens of dinosaur species, specimens, collected in the coastal region of mainly in Torres Vedras and Lourinhã, collected by José Joaquim here in this photo with my PhD supervisor, Francisco Ortega from UNED in Madrid. In 2008, José Joaquim asked this collection to management of the Sociedade de História Natural, and since then we start an exhaustive work to inventory and cataloging and study this collection. We also developed several excavation works to collect vertebrate fossils. This is one of the fossil sites that we have been working in Torres Vedras. In this locality, we found a partial skeleton of a large-size theropod, represented by an articulated section of a tail and an almost complete foot, besides several other more incomplete materials. This is other locality in Pombal, the Andrés fossil sites. In this locality, it was found in 1988, the first specimen assigned to allosaurs, known outside North America, and we resumed the excavation works in this locality between 2005 and 2010. And these works allowed the discovery of several new materials attributed to allosaurs, including abundant cranial elements. In total, this set of material represents about 80% of a skeleton of an allosaurus individual, representing the most complete theropod currently known in the Upper Jurassic of Portugal, and one of the few partial skull currently of a theropod known in Iberia. Beside these materials of allosaurs, it was also collected in Andrés several elements of other vertebrate groups, representing a very diverse fauna that includes crocodiles, pterosaurs, and different groups of dinosaurs. And this is an unexpected discovery in this locality. This is a specimen that belongs to a small sphenodontian reptile. This group of reptiles is nowadays represented by a single genus, to which belongs the tuatara from New Zealand. This discovery was surprising, not only because of the preservation of the material, but also because this is the first evidence of this group of reptiles known in Portugal, and one of the few evidences of these terrestrial sphenodontians known in the Mesozoic of Europe. So to study the phylogenetic or the relationship of the theropods, we follow the tools of cladistic systematics. So we construct data sets of morphological features that includes all the taxa previously described, and to which we add the specimens studied from the Lusitanian Basin. Then these data sets are analyzed with statistically based phylogenetic programs, which produce the phylogenetic trees with the most probable relationship among the represented taxa. These circles mark the position of some of the specimens that we studied from the Upper Jurassic of the Lusitanian Basin. And to construct these data sets, we review several of the most significant collections with Upper Jurassic theropod materials. The most significant are those of the North American Morrison Formation, the Tendaguru Formation in Tanzania, several formations in Asia, and isolated materials in other European areas. So we studied several of these collections to scoring and analyze firsthand the taxa based on firsthand analysis of the specimens. This is part of a collection from an institution that has material from the Morrison Formation in Utah, which is one of the most richest collection of late Jurassic theropods worldwide. This is other important collection from Tendaguru. This is some pictures of the Museum of Natural History of Berlin, where is housed the most important collection of dinosaurs from Tendaguru. These deposits of the Tendaguru Formation were studied for paleontological researchers since the beginning of the 20th century by German paleontologists, and after since the middle of the century by British teams. And these structures were used to transport the fossils during these first expeditions to Tendaguru. I just thought it's amazing, this kind of, it seems, fruit peel, and these blocks with mud material that actually is very similar to what we use nowadays with plaster to protect the blocks. And I'm going to show you quickly some of the material that we studied. This is medium and large size theropods. Some of the most abundant fossils of theropods in the Lusitanian Basin are isolated teeth. We studied about a collection with about 150 teeth, which were analyzed based on morphometric and multivariate statistical methods, which allow us to identify several morphotypes that belong both to medium and large size theropods and small, more derived forms, which are currently poorly represented in this record and for which the diversity is not well understood. This is other specimen that we described and that allowed the identification of a new species, Lusognathor santosi. That this species belongs to a group of theropods called Carcharontosauria, which is particularly abundant in the Upper Cretaceous of the South Hemisphere. And also in the Lower Cretaceous of Spain and England. But this material, this Portuguese material, represents the earliest evidence of these theropods in the North Hemisphere. And together with a taxon described in Tendaguru, represents the oldest, the earliest evidence of these theropods worldwide. So the identification of these species had significant implications to understand the early evolutionary history of these theropods, and particularly to analyze the first dispersion events of this group of theropods to North America and Europe during the Lower Cretaceous. Besides osteological fossil record, I've been also collaborating with in studies for analyze the ichnological fossil record of theropods and other vertebrates. These are some nice pictures of theropod and ornithopod footprints that we have recently described in collaboration with the colleagues of the Institute of Català de Paleontologia. And I've been also collaborating in the study of other vertebrate groups. This is a specimen recently described by my colleague Pedro Mocho, who was also from IDL, and that corresponds to a new species of sauropod dinosaur called Oceanotitan dantesi. Recently, I've also the opportunity to study some materials from the Lower Cretaceous of Spain and Portugal. The Lower Cretaceous is relatively poor in dinosaur remains, comparatively to the record of the Upper Jurassic. These are some of the materials that we study from the Lower Cretaceous of Spain, and that belongs to a specialized theropod, the Spinosaurids, characterized mostly by their crocodile-like morphology of the skull, which has been interpreted as related with aquatic or semi-aquatic habits of these theropods. The study of these materials...
Elizabeth, I'm sorry to interrupt you. Just to let you know that you should be wrapping up.
Okay, I'm going to pass quickly. So the study of this material allowed the description of these new species, Valibon natrix cani, and now I'm going to show you a little bit of the work that we are doing more recently. We already described preliminarily the vertebrate fauna in the Andrés fossil site. However, most of this material still need the full description and study. We are finishing now the description of all the material of allosaurs, and we are also preparing a project to study the neuroanatomy of these theropods based on 3D images obtained with CT scan equipment. These tools will allow us to access the morphology, the inner morphology of the skull, and to analyze some questions related with the paleobiology of these theropods. So just to finishing, the composition of the theropod fauna from the Lusitanian Basin is comparable with some paleogeographic models that propose the presence of intermittent land bridges connecting Iberia and North America in the transition between the Middle and Upper Jurassic. However, after this event, the establishment of geographic barriers, possibly related with the opening of the North Atlantic Ocean, would enforce mostly divergent evolution of the fauna in both sides of the North Atlantic. So we have closely related taxa, but that belongs to different species. These are some of the questions that are still open, such as why is there a stronger affinity of theropods from the Lusitanian Basin and Morrison Formation than those of other dinosaur fauna, and or what does explain the differences on the faunal composition among these areas. We are also trying to better know the fossil record of some areas of the Lusitanian Basin to which currently the record is less well known. And the main objective of this project is to understand this faunal turnover that occur in the transition Jurassic Cretaceous, and is marked by extinction of several forms and radiation of new groups. We are trying to modeling the diversity changes on this fauna during this time interval. So hopefully it will help us to understand these faunal changes. This is just some conclusions. I just want to underline the significance of the fossil record of the Lusitanian Basin to understand this evolutionary history of this fauna, and just thank to several institutions and people that have been supporting these works, and thank you. And I'm sorry for the slide.
Thank you, Elizabeth. Yeah, lots of material, lots of very interesting. I think we have to skip the questions for now. We will go straight to Francienne's presentation, and then if we have some time afterwards, we will. Okay, is that okay, Francienne?
Sorry, okay.
Yeah, go ahead. You can share your screen.
So I am Francienne, and I will present the hydrological modeling applied to water resource management, which is the research subject that I have been working in the last years, especially in the doctorate and the postdoctorate, developed here in Brazil and in Portugal. It's known that the water is the most wide
Francine, I'm not, at least from my end, I'm not hearing you. I think your connection might be down. So I think we're experiencing some technical difficulties. Yeah. Okay, it's not only me. Let's see if she can rejoin us. Hi.
Sorry, I think it's connected.
Yeah, I think your connection went
Here
down.
now?
Yeah, we're seeing the slides.
I'm sorry. I think he was here.
Yeah.
Yeah, in this way, the uses provided by this research are multiple, but in many regions of the world, they are not able to meet even basic drinking water and sanitation needs. This situation happened because water resources in the world have become increasingly polluted, damaged, and have been decreasing over time in terms of quality and quantity due to factors like the excessive population growth that not only severely reduce water availability per person, but also create excess on biodiversity in the entire global ecosystem. The water pollution that occurs when substances contaminate the water resource, degrading water quality and rendering it toxic to humans or the environment. The irregular urbanization, mainly near rivers, that has caused many environmental problems, especially the serious deterioration of water quality, and the excessive industrialization that produce pollutants that are extremely harmful to people and the environment. And this, in this sense, water and river-based management systems are created to avoid, prevent, or resolve conflicts among multiple users who depend on the water resource. Thus, water dynamics understanding a watershed is fundamental to water resource management. A watershed is an area of land that drains water into a specific water body. This area has several fundamental characteristics, such as the interaction between abiotic and biotic factors, the anthropic interaction, and the inherent impacts of its activities. Anthropic changes in hydrology and in the natural characteristics of river basins can, among other things, significantly influence the ecosystem, environment, the economy, and cause negative impacts such as economic damage, material damage, loss of life, and contamination of water supply. In this sense, hydrological models are among the available tools used to predict the quantity and quality of water in a river basin for decision makers, and can predict the impacts of natural and anthropogenic changes on water resources, and also quantify the spatial and temporal availability of resources. However, choosing a specific hydrological model for a river basin and management according to the study objective is challenging. Hydrological models are widely used tools around the world in research and water resource management, since they enable the understanding of natural processes and find solutions to environmental problems. These models are essential in the water resource management and are typically used to assess the hydrological behavior of river basins in many applications. As we can see in this image, the hydrological models can be used to evaluate the water availability and the dependence on factors as climate or land use change. Hydrological models can be classified according to the spatial variability in concentrated or distributed model. There are also a semi-distributed model, like we can see in this image. The form of representation of the data in discrete or continuous model, and the type of variables used in modeling in stochastic or deterministic models. Several useful hydrological models are available today. The models have many different sources for watershed assessment. Some of the hydrological models available include, for example, the agricultural point source pollution model, the environmental policy impact calculator, and the soil and water assessment tool. Regarding the SWOT, the soil and water assessment tool, this model was developed by the Agricultural Research Service by the United States Department of Agriculture. It's a physically based watershed scale, continuous time scale model, which operates on a daily time step. The SWOT model can be used to simulate the quality and quantity of surface and groundwater, and predict the environmental impact on land use, land management practice, and climate change. SWOT is also widely used when evaluating soil erosion, no point source pollution control, and regional management in watersheds. In the SWOT model, the watershed is divided into sub-basins based on topography, and then each sub-basin is conceptually subdivided into hydrological response units, the HRUs, which have a unique combination of soil, land use, and slope. Here are same examples of elevation data, soil types, and land use from one of the study areas that I worked here in Brazil, in São Paulo State. In this manner, the model uses meteorological data, elevation data, soil types, and land use to calculate the daily flow, sediments, and balance of contaminants in a watershed. So in my doctorate, we developed a comparison study between the concentrated hydrological model and the SWOT model to estimate the stream flow, water quality, and sediment yield in two river basins located here in São Paulo. Regarding the SWOT model results, as we can see in this image, the model was able to adequately simulate the general stream flow variation in a daily time step, as well as its minimum and maximum values. The SWOT model was also used in my last paper published, which is part of the postdoctorate that I developed here in Brazil and in Portugal. The paper is Effects of Land Use Changes on Stream Flow and Sediment Yield in Atibaia River Basin, here in São Paulo, is the second basin here in this image. The main objective of this research was to evaluate the impacts of changes in land use on the stream flow and sediment yield, and to analyze all SWOT parameters related to land use and determine the most important ones. Two different land use change scenarios were applied to the study basin, where the SWOT model was able to predict the effects of land use changes on the stream flow and sediment yield. Now, the main research interest already started at IDL is the application of the SWOT model in Portugal. The main objectives of this research are
I think we lost Franciane again. Well, this is the caveats of allowing the presenter to, to share the screen.
Sorry,
okay, she's back. Hello.
Yes. But I think it's possible to see the end of the presentation. Hello?
Yeah. Go ahead.
Hi.
Yeah, you can share it. Yeah.
I think I stop here in the last slide.
Yeah.
Yes, now the main research interest already started. The IDL is the application of the SWOT model in Portugal. The main objective is to access the water availability using SWOT model on the current and climate change scenarios, to understand the agroforestry sector, and to simulate adaptations measure that will minimize the impacts of the climate change. The input data has already been extracted, and we are now starting the simulation stage. Is this? Thank you for attention.
Thank you, Franciane. So we have a couple of minutes to answer some questions. Yes, we have Rita Carvalho.
Hello, very nice presentation. Thank you very much. You mentioned the sediment yield. Are you planning to compute the sediment yield here in Portugal also in this application or not?
I think in this moment now, no.
But could be a future step?
I think it's a plan for the future, yes, but not now. Now it's only the climate changes scenarios and the...
Because the climate change is also important in the sediment yield, and this is very important for the coast. And so I think that we could benefit from this approach. Perhaps Francine cannot solve every problem, but in collaboration could be a very nice post-development of your work. Thank you very much.
Yes, I agree. Thank you.
Thank you, Rui. Any more questions? Okay. So it's 10:30, I think. Yeah.
Did you validate the sediment yield in your application in São Paulo?
Yes, I tried, but the monitoring gauges, they have only be monthly monitoring. It's so difficult to validate these data.
Okay, perhaps you could have some experiments on that, because this is a very also difficult task in calibration, these kind of models. C3C, as a person that is working with the experimental plot, and perhaps it would be a very interesting site to validate your model. We have to talk afterwards. Thank you very much.
Okay, thank you.
Okay, so I think we'll carry on with our presentations. I'm going to share my screen now. I will start asking Afonso Gomes. I think he's our first presenter. Yeah, Afonso, are you there?
Yeah, I'm here.
Hello.
Hello.
Okay, go ahead.
Okay. Good morning, everyone. My name is Afonso Gomes. I'm doing my PhD here at IDL. My work is on the numerical modeling of Tethyan type ophiolite emplacement, and it's being supervised by Filipe Rosas and João Duarte, also from IDL, and from and Nicolas Riel from the University of Mainz. Next slide, please. So just as a context and as a quick recap, this is a schematic of the general geodynamic cycle of the oceanic lithosphere. So the oceanic lithosphere, as it ages, it thickens and it cools, becomes denser than the underlying asthenosphere, and eventually becomes gravitationally unstable and is consumed in a subduction zone. This subduction is the fate of 99.99% of the volume of all oceanic lithosphere that is generated at mid-ocean ridges. Okay, next slide, please. Next. But in my study of ophiolites, I'm interested, this one. I'm interested in the 0.001% exception, that is the portions of oceanic lithosphere that somehow avoid subduction and instead get placed on top of continental lithosphere. These are called ophiolites. Next, please. So this begs some really big questions, which is, how is it possible for a denser oceanic lithosphere to avoid the subduction and instead end up on top of less dense continental lithosphere? What are the special geodynamic circumstances that are needed to produce this occurrence? Next slide, please. So there are actually 5 known modes of ophiolite emplacement that are known only not very well. I'm only going to talk to you about the most important one, which is Tethyan ophiolite emplacement. It is called Tethyan ophiolite emplacement because it is the mechanism responsible for the emplacement of the ophiolites from the Tethyan Ocean. Next, please. So this is a schematic of this process. The ophiolite starts out as a forearc or as an oceanic overriding plate in a subduction zone. The subducting slab has a continental margin trailing edge, as you can see here in image number 1. And as the subduction progresses, the slab pulls the continental margin beneath the overriding plate and future ophiolite. And then there's a slab breakoff and eventually an isostatic compensation, an isostatic rebound from the continental margin, completing the emplacement process of the ophiolite. And next slide, please. So this is exactly what I want to model using the underworld numerical code. This is a schematic of some of the models we are running. At first, we are particularly interested in studying the parameters that have to do with the continental margin. So for example, the margin has to be strong enough to sustain a partial subduction without breaking immediately, but yet weak enough to bend into the subduction channel and to not overly deform the overriding plate and the ophiolite. So next, please. Next. So this is still very much a work in progress. This is just a sneak peek of a model that I'm running. It does not yet reproduce the continental, the plate breakoff, but it does represent the partial subduction of the continental lithosphere beneath the overriding plate. Next. Okay, thank you for your attention.
Thank you, Alphonse. That was very clear. We will go straight to the next, and then at the end we will compile all questions so that this can run smoothly. João?
Yep.
Hi. Hello, good morning.
Hello, good morning.
Go ahead.
Well, I'm João Geodynamic. I started my PhD 5 months ago, and this is the theme of my project, so assessment of the concurrence of heat waves and droughts in Southeast Brazil under present and future climate change conditions and impacts on public health. I have as supervisors the Professor Ana Augusto, the Professor Hadley Cells, and also the Professor Diego Miralles. So this is a joint project in the sense that I will perform part of my work here in the Institute of Luís, but I also intend to spend some time in Brazil at the Federal University of Rio de Janeiro and also a few months in Belgium in the University of Ghent. So compound hot and dry events have gathered great attention over the recent years. Several recent studies have proved that there's a great potential to drought conditions amplify temperature anomalies during heat waves through soil moisture temperature coupling mechanisms and generating the occurrence of massive mega heat wave events that have harmful impacts in public health and more specifically in generated high levels of heat-related deaths and also high levels of hospitalization. So the main objective of this PhD is to highlight all these aspects for the Southeast Brazilian region. Well, and why Southeast Brazil? Well, because Southeast Brazil is a very heavily populated region of Brazil. It encompasses the metropolitan regions of São Paulo, which, by the way, is the 4th largest and most populated urban area of the world. And it also encompasses the metropolitan regions of Rio de Janeiro and of Belo Horizonte. And also, in an economic perspective, this is a very important region for the whole Brazilian economy. In addition, unfortunately, there is still an absence of analysis and studies highlighting this topic for the Southeast Brazilian region and for all South America, not just Brazil. So we strongly believe that this PhD is of extreme importance to fill all these gaps. Can you please move forward? Thank you. Okay, so I decided to show you the 4 main objectives of this project. The first one is to characterize the historical incidence of compound heat waves and droughts in Southeast Brazil. This, in fact, this topic was already accomplished with success. The second one is to unravel the physical processes associated with compound drought and heat waves. And for this, we'll have to consider meteorological and conditions at several temporal and spatial scales. This is a topic that I'm currently working. The third one is to establish the link between the heat stress conditions during the occurrence of compound hot and dry events and the impacts on public health. And for this, we'll tend to use statistical regression models to quantify the degree to which concurrent extreme hot and dry atmospheric conditions will affect public health, and more specifically, the number of heat-related deaths and the number of hospitalization for these 3 urban regions of Southeast Brazil. And finally, the fourth one is to assess the impacts of future climate change scenarios on concurrent heat waves and droughts for these Brazilian regions. And for this, we intend to use the Cortex model experiments. Can you please move forward? Yep. So I decided to show you some results that fit within the first topic. Here we have for the Southeast Brazil, the percentage of change of the occurrence of compound heat waves and drought events for Southeast Brazil for the period between 1980 and 2020. And we can clearly see that some regions have recorded an increasing trend in the occurrence of these compound events, even considering different heat wave thresholds for the heat wave definition. And in fact, the regions marked by black crosses indicate the grid points in which these percentage change were statistically significant at the 5% level. Can you move forward, Hannah, please? And we were also able to verify that most of these increasing trends were explained by the number of concurrent drought and heat wave events that have been recorded during the most recent summer seasons in Southeast Brazil, more specifically during the austral summer seasons of 2013 and 14, and 14 and 15, and we defined as austral summer seasons the periods between December and February. Can you please move forward? And yeah, for those who are interested in looking in more detail for these analyses and results, I encourage you to have a look on this paper that we published in February 2021, Environmental Research Letters, that highlights with more detail all these aspects. And yeah, that's it. Thank you very much.
Thank you, João. That was very nice. Moving forward, we have Rita Carvalho. Rita, are you there?
Yes.
Hello.
Hi, everyone. Thank you so much for this opportunity. It has been great to see what everyone is working on. My name is Rita Carvalho. Just a little background about myself. I graduated in biology and have a master's in biology and geology. And prior to this adventure, I worked for a couple of years in a hydrogeology consulting company. So my advisor and I thought this was the perfect topic for my PhD, which is hydrogeology of Portuguese sulfurous waters in distinct geostructural contexts, a multidisciplinary approach. Next, please. So the main question we want to solve is, what is the origin of the reduced sulfur species present in the Portuguese alkaline sulfurous waters located in the Esperic Massif? This is northern and central Portugal. There are some researchers who explain its presence through metallic origin, while others consider that its origin may be related to sulfur-reducing microorganisms. This is where microbiology enters the room. To answer this question, we chose three thermal sites in different geological contexts. We chose Caldas da Rainha in a sedimentary limestone environment, and Unhais da Serra and Vizela in arsenic granites, but they are associated with different fault systems. To fully understand this context and to be able to answer the initial question, we are using, as I said, a multidisciplinary approach that encompasses several disciplines such as geology, hydrogeochemistry, hydrodynamic, and microbiology. This is with the objective of obtaining a flow model and defining the recharge area for each site. And then with the final conceptualization of all this data to comprehend the hydrogeological functioning of these localities. Next slide, please. I'm at the beginning of my third year, and we have done microbiology sampling, but only in Caldas da Rainha. We are digesting the results now. Pumping tests and its interpretation, chemical and geological characterization, and fault and lineaments survey. Of course, all of this with a never-ending bibliographic research. I think I underestimated the work that had to be done in order to comprehend fully the knowledge from all these disciplines and the pandemic and all. Instead of just 3 years, I think I'm going to need 4. So that's it. Thank you.
Thank you, Rita. It was very, very nice. Next, we have Viviana Belvede.
Yes, I'm here.
Hello, good morning.
Hello, good morning, everyone. My name is Viviana Belvede. I'm a second-year PhD student in external geodynamics. The theme of my PhD work is using the morphology of insular shelves as a key for understanding the geological evolution of the Oceanic island, the case study of Madeira Island. My supervisor are José Madeira from Instituto Dom Luís, Rui Partau from Instituto Geográfico, and Claudia Romagnoli from Bologna University. Next slide, please. Okay. Before moving to Lisbon, I studied at Bologna University, where I achieved my bachelor degree in geology science. And my final thesis was about the stratigraphy and depositional process of pyroclast of the green tuff at Pantelleria Island. Then I continued my study in geology and land management, and my final thesis was about the morphological and morphometric study of the Sambari volcanic cones of Linos Island. Next slide, please. Now my PhD project focuses on the southern insular shelf to better comprehend the evolution of Madeira Island using data such as multi-beam bathymetries, seismic profiles, and sediment samples. Especially the thesis is divided in different sub-studying, starting first with the bed form characterization, then with the shelf sedimentary dynamics, next with the seismic stratigraphy and characterization of the clinoform bodies, and finally with the formation and evolution of the southern insular shelf. Next slide, please. During my first work year, I analyzed the main bedform field on the southern shelf, and you can see an example in this map. And I could observe that this bedform field developed of short stream mounts or high cliffs, and where the shelf has a slope more than 4 degrees, and where there is a significant fine sediment fraction. These fields are inside a channelized or fan-shaped feature, and from their morphological and morphometric characteristics, together with the multitemporal bathymetry observation, I can say that they are probably cyclic steps, a type of seafloor ondulation attributed to the occurrence of a turbidity current, probably triggered by flash flood or stormy events. And that's all. Thank you for your attention.
Thank you, Viviana.
Thank you.
Next, we have Danielle Santos. Are you there, Danielle?
Yes.
Hello, good morning.
Hello, good morning.
Go ahead.
First of all, thank you for the invitation to present my PhD research, which is called Development and Performance Maximization of Flexible Polymeric Films for Energy Storage in Sodium-ion Batteries and Supercapacitors. Next slide, please. As you know, one of the most batteries that our daily appliances used are lithium-ion batteries, but the abundance of lithium resources in the Earth's crust is decreasing year by year. So we need to start thinking about alternatives to lithium-ion batteries. And one of the best alternatives are sodium-ion batteries, because sodium is very abundant in the Earth's crust. Also, the materials for a sodium-ion battery are cheaper than lithium-ion batteries, and also we don't have the non-economical need of recycling the battery electrode materials. But sodium-ion batteries have two big problems. One of the is the lower specific energy, because as you know, sodium is heavier than lithium, and also due to the large ionic radius of sodium compared to lithium, we have the difficulty of developing cathodic materials because it is impossible to sodium be intercalated in conventional cathodes that are used in lithium-ion batteries, for example, perovskites and spinels. So my research topic is to develop a flexible material. Next slide, please. Another one. A flexible material using a conducting polymer. In this case, I'm using the PEDOT PSS because this material can expand and contract during the redox conversions. So it is capable of incorporate sodium during the battery's redox processes. And also we can have an intake and an outtake of sodium without damaging the structure. Next slide, please. Now I'm going to present three results of my study. The left figure shows a potentiostatic synthesis of the conducting polymer at different temperatures. In this potentiostatic synthesis, we applied constant potential during a certain moment of time. And as you can see, for higher temperatures, we have higher current. Also, it is important to refer that these polymers, these three polymers, have different matrices. On the right figure, we have the redox behavior of the synthesized polymers. This redox behavior is an electrochemical characterization in organic medium. In this case, I used sodium perchlorate in acetonitrile, and as you can see, for a polymer which is synthesized at higher temperature, we have bigger current densities, and also it is important to refer that we have more charge and more electroactivity. Also, you can see three oxidation peaks and three reduction peaks. The first oxidation and reduction peaks is due to the intake and the outtake of sodium ions during the redox conversion. The other oxidation and reduction peaks are just the polymer conformations. On the table, it is a study that I did by ellipsometry, then which can give us the refractive index, the extinction coefficient, and also the thickness of the material. And as you can see, for higher temperatures, we have more material, and our conducting polymer have more conductivity, but is also less dense than a polymer synthesized, for example, at room temperature. So this is an important result because at different temperatures we can produce a different type of materials that can do what we want, and they can be more specific for for an appliance than the other one. So for less dense materials, it can be used on a supercapacitor, but for denser materials, can be used in a cathode for sodium-ion batteries. Next slide, please. Thank you all for listening.
Thank you, Danielle. That was quite a bit of a change of subject, which is great also to show the different branches. Next, we have Teresa Silva. Are you there, Teresa?
Hi, yes.
Good morning.
Good morning. So, my name is Teresa Silva, and I am in my second year of the PhD, and the title of my thesis is Harmful benthic dinoflagellates from Madeira Archipelago in a Changing Ocean, Ecology, Systematics and Toxicity. I am supervised by Professor Ana Amorim from Maré, Professor Manfred Kaufmann from the University of Madeira, and Dr. Philip Hess from IFRMR Nantes. Next slide, please. So I live in Madeira now. I came here 5 years ago, and I work basically in the Phytolab, micro phytoplankton lab from the University of Madeira. That is, it's in the Estação de Biologia Marinha do Funchal. Basically, I work with phytoplankton with very small microalgae. Next slide, please. So I don't know if you heard about red tides. Red tides are caused by phytoplankton, and they appear when the light, temperature, or nutrients are in optimal conditions. Then they bloom. They massively proliferate and cause this kind of tides. If we are talking about toxic species, they can cause biological hazard. So it has impacts on the human health, on tourism, aquaculture, and fisheries, and marine fauna. Next, please. The main causative species are Gambiardiscus and Ostreopsis. Gambiardiscus produces ciguatoxins that causes ciguatera fish poisoning, and Ostreopsis produces paleotoxin that is a potent neurotoxin, and it causes respiratory syndromes. Both species or genera and can cause human death, and several people, thousands of people already died from exposure to these toxins. In Madeira Island, the first bloom of Ostreopsis was observed in July 2013. Next, please. So, in the Cais do Carvão Bay, southeast Madeira Island, where this bloom was detected, we are making a monitoring plan to analyze what's going on. And the questions we ask are: which BHAP species are present in Madeira Island, the abundance, frequency, and seasonality, and are these species toxic, and which environmental triggers causes the blooms and the toxicity, and how do environmental variables affect the presence and the spread of these groups of microalgae. Next slide, please. So we did this monitoring in the Cais do Carvão Bay, and we we studied the biology of barb communities, and also the physical chemical parameters. Preliminary results indicates that we have 5 genera present in the waters, in the water column: Amphidinium, Protocentrum, Culia, Ostreopsis, and Gamberdiscus. Ostreopsis was always the main species present, genera present in the water column. And the values we detected for Ostreopsis were very high. Tester et al., they defined some limits that are represented in the graph in red. And if you can, the bars, the blue bars represents Ostreopsis, and we exceeded those danger limits by far. Next slide, please. So this happened in 2018, 2019, and 2020. We have the same, basically the same profile during the summer months, when temperatures are above 23 degrees. This kind of blooms occurs. Next slide, please. So the next step is to investigate if the genera that are present in Madeira waters are toxic or not. So we are going to do toxin profiling, and also investigate the physiological traits. And we intend to do also ecologic studies in order to see how these species respond to climate changes. Next, please. Next. Thank you. It's all.
Thank you, Teresa. It is very interesting. Another small shift in theme, which is always nice. Next, we have Osório Cavacundo. Osório, are you there?
Yeah, I'm here.
Good morning.
Morning. Okay, here we go.
Go ahead.
Morning, everyone. My name is Osório. Please, next slide. Osório de Cavacundo, and I'm from Angola. Please, next, and next, and next again. I'm from Angola, where I did my graduation in physics, and then I came to Portugal to do my master degree in Évora University. And right now I'm working here in FCOL in a project entitled 3D Seismic Structure and Crustal Evolution of Southern Portugal. And I'm working with Professors Luís Matias and Nuno Dias. We have just started this project in December 2020. I mean, it is mostly in January 2021. Please, next slide. There are two work that serve as basis for this project. One is from Matias, 1996, and one of the conclusions of this work was that the azimuthal variation of P velocity in South Portuguese zone can be explained either by an anisotropic model or by a damping layer. And that means that the causes for the anisotropic property of the soft upper crust of South Portuguese zone is not well understood. So he proposed to perform a high resolution tomography. Please, next slide. Next. So recently, Veloud et al. Performed tomography and seismicity studies for the mainland country, the whole mainland country. And for the South Portuguese zone, they found that the seismicity present a diffuse pattern to the east, and orientation and a cluster around Mochique to the west. Also, please, next slide. Also, they conclude that the seismic heterogeneity in a South Portuguese zone present no apparent correlation with the surface geology. Please, next slide. With this in mind, we propose the present project to achieve the following goals. One is to elaborate a high-resolution 3D tomography, and we will pay particular attention in areas around Serra de Mochique. Please, next slide. And the second objective of this work is to investigate the anisotropic property of the upper crust or lower crust, if possible, which are referenced in the previous works. Please, next slide. And the last objective is to make correlation between the 3D structure with the seismicity, tectonics, and with the crustal deformation. Please, next slide. We are working based on this methodology as presented in this slide. And one of the things that I may highlight here in this slide is that it is necessary to make a compilation of all seismic data from different sources, active and passive ones, for the South Portuguese zone. There are a lot of data from different projects that were collected during a long time. For example, the passive data, where some of them were collected from 1919, 1917, and on. And we will collect these data and make a database to then perform our tomography. Throughout this process, we will try to write at least three papers. If it's possible, more we can write. Please, next. Next. But for now, we have just collected the last stations from Mochique's temporal network, and we are working on this data. Please, next slide. We are working on this data, making the quality control of this data to see the availability of this data. Those are the last data that we must join to the data that already exists. Please, next slide. And also we are starting to do the event identification with the spectrogram. That's what we are doing now, and I don't have results to present because I've just started this work in January, and we are work on this to go further. And that was possible to show you in a few minutes. And thanks for your attention.
Thank you, Osorio. I thank you for your patience. This was a very nice presentation, but remotely it doesn't work so well. Thank you.
Okay.
Thank you. Next, we have Jesus Reis.
Hello.
Are you there, Zeus? I've heard you, but I don't see you.
Sorry. Now?
Yeah, okay, hello.
Okay, thank you.
Go ahead.
Hello, everyone. My name is Jesus Reis, and the title of my thesis is Internal Wave Generation and its impact at the island shelf. My supervisors are Professor Miguel Bruno from University of Cádiz, Professor Álvaro Plis from University of Lisbon, and Dr. Rita Carvalho from Arditi. Next slide, please. The first time I saw this figure, I thought this was to be my PhD thesis, because no one until now had studied this type of wave here in Madeira. This internal wave has a considerable scale comparing with the island, and also it has influence on the coastal dynamics and enrich the oligotrophic waters around the island. Next slide. In my thesis, I have four main objectives. The objective A, the implementation of non-hydrostatic model in Madeira Island. The model chosen is the non-hydrostatic Croco model. The objective B, the assessment of the generation of internal bore around the seal on Ponta de San Lorenzo. The objective C, the study of the internal wave resulting from the interaction with the Madeira Island shelf, such as coastal trapped waves. The objective D, the impact of the wave, the internal wave on the coastal zone. Next slide. On the east of Madeira, between Ponta de San Lorenzo and Desert Islands, there is a submarine ridge, and due to the interaction between the tide and this submarine ridge, a type of solitary internal wave called solitons, it's created. At this moment, we have here we have a configuration of a co-host model with a spatial resolution of 300 meters and a temporal resolution of 30 minutes. And this configuration is able to represent the internal waves. As we can see here in the figure, where we observe the oscillation in the isotherms due to these internal waves. Next, please. Here we have represented the depth of the 18 degrees isotherms, and we can observe this wave propagate to northeast toward Porto Santo Island, and it happened every 12 hours. And with this, I finish my presentation. Thanks for the attention.
Thank you, Jesus. Very nice graphics there, and very interesting subject too, although complex.
Thank you.
Next, we have Joel Seferino.
Yes.
Hello, good morning.
Hello, good morning. So, good morning, everyone. I have been a PhD student here since last year.
Sorry, Joel, I made a mistake. Yeah, I'm sorry. I was trying to shut me up and.
No problem. My research topic is methodology to sustainable management support of groundwater resources in regions under anthropogenic stress and climate change, numerical model versus artificial networks. Next slide, please. Next, sorry, I put too many animations. So I graduated from Nova School of Science 4 years ago. I have a master's degree in geological engineer. And since then, I've been a research fellow here at a university in the field of hydrogeology. I was involved in several projects. I would like to highlight two of them. In the first one that we see here, we studied the recovery time of groundwater contaminated by nitrates of agricultural origin. This, I think, was Estarreja Mortosa is one of the 9 vulnerable zones that we model. Next, please. In the second one, we did the review of parameter protection from groundwater wells, public groundwater wells, in the scope of new Montijo Airport. We studied the possibility to move these abstractions to other locations away from the project layout. Next, please. So my research topic is this. I think the title is too long, it's self-explanatory. Next, please. I will use these two approaches to try to predict variations in piezometric levels. One more common, like a numerical model, but so to speak, is not always the answer. It can be very tricky to implement in complex conceptual models. So I will also use artificial neural networks to predict this. We're going to train and validate based on historical records and based on that, try to predict the variations on piezometric levels. These are some of the goals that I will try to achieve. I'm going to do the analysis of pre-processing steps of both methods, determine the associated costs and consumption time, basically the degree of difficulty, if there is some complementary in both methods, and if you have different outputs, I hope so. If not, why? Next, please. Yes. The study area is a small portion of the Tagus Basin Aquifer, margem esquerda do Tejo, aquífero da margem esquerda do Tejo. There is not, I think, a better translation. In a small peninsula in Montijo Alcochete, it's a coastal and also an urban area that we're going to have a huge possibility of population growth, and it sits next to the Tagus estuary. Next, please. There's one more. So far, I don't have a background in IT or computer science, so I spent these early days attending courses from the Masters in Informatics here at the university. These are some of the examples. The typical state-of-art process, one more please, and setting up the hydrogeological conceptual model. There is one adopted at the regional level. I think locally can be some difference. So far we are able to identify 3 aquifers. One more, please. One more, thank you. There is some data missing. I think it's not the best time to ask someone if he can enter their house to see the wells, the abstractions in this time. But we are able to show the first piezometric level that we can consider somehow actual. And for now, the piezometric levels are below the sea level. And we are also to find out that is possible a hydraulic barrier in this site caused by a geologic fault that is restrained the groundwater flow from east to west. And I think it's all. I think I forgot something. I didn't put my supervisors in the first sheet. So is Rosario Carvalho here from the university, also with Professor Luis Correa, and from Nova Professor Maria Manuela Simões. Thank you. That's all.
Thank you, Joel. Very interesting subject too. Now we pass on to Simone Innocentini. Simone, are you there?
Okay, can you hear me?
Yes. Go ahead. Sorry, now we can't hear you. You have your micro. Yeah.
No, okay, sorry.
Yeah.
Hi, I'm Simone Innocentini from Italy, and my PhD is in external geodynamics with the title of Gravitational, Erosional, Sedimentary and Volcanic Processes on the Submarine Environment of Flores and Corvo Island in the Azores Archipelago. The project started last February and it's joined between Lisboa, Istituto Idrografico and the University of Rome La Sapienza under the supervision of Professor José Madeira, Rui Cartau and Professor Daniele Casalbore. Next, please. The project wants to improve our knowledge of the geological evolution of volcanic islands using both of new onshore and offshore datasets, and it has also an important social and economic relevancy for what concern, for example, hazard assessment and evaluation of marine resources. For doing that, I'll characterize the shelf morphologic parameters, the underwater lava flows, sedimentary cover, shelf edge collapses, and submarine tributary systems. Also making a comparison with islands subaerial evolution and with other islands settings. And I will try to formulate conceptual models of the evolution of shelf and submarine flanks. Next, please. These are the Flores and Corvo Islands. They are at the northwestern termination of the Azores archipelago. For example, the social impact. For the social impact, we know that from the bibliography that in 1857, a massive fall in Flores Island caused a local tsunami and 10 deaths and a lot of damage and injury between the two islands. I'm not able to show any results because the first survey will be probably next June, and then it will be followed by other surveys. But here we have an example of the shelf of Santa Maria Island that has already been studied by Ricky et al. Next, please. And this is my education background. As you can see, I've already worked for the Istituto Idrografico during my master thesis in 2 years ago, 1 year ago. And for that project, I've worked on data from the southern shelf of Porto Santo Island in Madeira Archipelago, making a characterization of erosional, depositional, and gravitational processes. And some results will be published hopefully soon in a first paper. And also last October, I've also joined a scientific cruise organized by Gerhard Bormann from the University of Bremen, looking for mud volcanoes and gas bubbles flares in the Mediterranean Sea. Next one, please. Thank you.
Thank you, Simone. I hope you enjoy the Azores, some of the finance landscapes in Portugal. In my humble opinion, of course.
Thank you.
And finally, we have Carolina Rocha.
Yes.
Hello, good morning.
Hello. Good morning. And you can skip the first slide, please.
Okay.
Good morning. I am Carolina Rocha, one of the new PhD students, and my thesis title is a multi-scale coastal risk assessment due to sea level rise on the Atlantic coast of mainland Portugal. As this team follow up my previous research, on the next slide I make a brief presentation. I obtained my degrees here at Faculty of Science, and in my master degree I studied the physical vulnerability to sea level rise. It was done on the national scale with a spatial resolution of 20 meters. And after that, I embraced the challenge of participating in some projects where similar cartographies were produced for Portuguese municipalities and companies with private funds. These cartographies have a higher spatial resolution in the order of 10, 2, and 1 meter. Next slide, please. Next and next. Thank you.
I want to show you our website. Feel free to consult him. It was created with the purpose of publish the national study, but also sensitize public opinion. On this website, you can find different cartographies: extreme flooding due to extreme events, high tide flooding, physical vulnerability, and some demographic statistics. Next slide, please. So my current challenge is PhD. I started last December, and I'm delighted to presenting my supervisors, all from FCUL, Carlos Antunes and Cristina Catita from IDL, and Professor João Gomes from Statistics Department. Next slide, please. The main motivation comes mainly from the transposition of the European directive, the Floods Directive, which impose for each national institutions to prepare risk cartography with the maximum positional accuracy. And with that, it will be possible to identify the areas of greatest risk. Next slide, please. Next. Thank you. No. The following objectives will be achieved based on the multi-criteria decision analysis and considering each projection scenarios of sea level rise. The methodologies and respective cartographies will be developed for hazard and physical susceptibility, a multi-scale methodology for the coastal risk index where socioeconomic data will be used. And what is the cost of doing nothing? How much will it cost to keep my city safe? To answer these questions, I pretend to develop a methodology of the evaluation of economic damage using, for example, property value and other data, and develop a process of the emergence of adaptation, namely define adaptation phases in case studies of the areas previously identified. And finally, publish the research in different channels. So thank you for your attention.
Thank you, Carolina. It was very nice to have your participation in geoinformation. I think it was the one subject, one of the few subjects lacking here. So with this, we have ended our PhD presentations. I'm going to stop sharing my screen. And now I will ask, we have a couple of minutes before coffee break, if there are any questions either regarding the PhD students' talks or perhaps about Elizabeth's talk earlier. No? No questions?
Can I do a question to one of the PhD students?
Yeah, sure.
To Viviane. Is Viviane there?
I'm here.
Yeah. Hello, Viviane. Thanks for the presentation. One question, though. The scour marks you showed and the submarine canyons are really nice. Do you think you will have surveys from different times in order to compare the evolution?
Well, I compared two different bathymetries from 2013 and 2019, but they are not complete. So just for some bed from field, I can compare the structure. And it was really interesting see that in the bed forms there are an alternation of erosion and deposition on the surface. So for this also for this reason, I can say that probably cyclic steps.
Okay, thank you so much.
Thank you.
Thank you.
Oh, good. Any further comments, questions? Maybe I can ask Jesus a question, if Jesus is there, Jesus Reis.
Yes, I'm here.
Yeah. I was wondering if in your study you're going to use SAR imagery to observe the internal waves around Madeira.
Yes, it's one of the objectives. Use satellite data, because but we don't use yet.
Yeah, for sure. Just to maybe to have an idea of. You already know that it's like a 12-hour kind of current, right?
Yeah, it's 12 hours, but the problem is we have proved this 12 hours with in situ data, but not. But it's preliminary results yet.
Yeah, for sure. Just a curiosity. Okay, so it's 11:30. So coffee break now, and we'll be back here at 11:45 for the IDL Awards symbolic ceremony, and then for the invited talk at 12 by Michael Bay. So see you soon. Hello.
Hello. We have to make sure that the nominees are here.
I think they are. Let me just check. If maybe they can, I'm starting to see them. Yeah. If you can turn on your cameras.
Posso só sugerir uma coisa? Depois, quando for a apresentação do Michael, era fixe se algumas pessoas pudessem ligar a câmera. Porque a apresentação vai ser para aí meia hora, 40 minutos, e estar 40 minutos a falar para um quadro preto não é muito motivador.
Acho que sim também.
Se alguns puderem ligar, acho que era fixe. A ideia depois também é ver uma discussão no final, acho eu.
E ver a reação da audiência quando são ditas determinadas coisas, a malta lá.
Não é. Agora têm sido curtinhas, não é? Têm sido curtinhas até.
Mas é verdade.
Mas nas longas uma pessoa aborrece a si própria e depois. E é um bocado isso, a dinâmica depende muito das reações, especialmente quando são palestras de coisas longas.
Ainda mais importante no estado remoto, não é?
Estas reações são muito pouco expressivas, as reações do Zoom, não é?
É isso.
Tens os smiles.
Olá a todos.
Olá, Jorge.
Isso é verdade, Francisco, de facto. Mas ele pode ter o. Se eu bem conheço, ele deve ter para aí 3 devices ligados ao mesmo tempo.
Pode ter uma só para ver a audiência.
Um é investigador da NASA, ele ontem disse. Ele mandou uma apresentação e disse: tenho 2 computadores preparados, o iPad e o telemóvel, em princípio não deve correr mal, mas correr mal, depois partilhas tu. Portanto. Eles põem drones a voar em Marte, portanto estão habituados à redundância.
Se correr mal, tem uma ligação de satélite dedicada, não é?
Capaz.
So shall we get to the IDL Awards? I will be sharing my screen, but I will let Rui do all the talking.
Okay, so thank you very much for being here. This is a very symbolic, but I think important moment. And for me, it's really a pleasure and an honor to present the IDL prizes. This year, I don't know why, we didn't have any submission to the travel award. People don't want to travel in Zoom, so they don't want a travel award. But on the contrary, we have very, very good submissions on the IDL prize. There was a lot of submissions for the best PhD at IDL, and that poses a big trouble to the jury, because at first, when we developed these prizes, we thought to give 1 prize, then we start to give 2 prizes, and now we are on the 3 prizes, and even so, the others that didn't receive the prize are very, very good PhD, and not only the PhD, but I think also the PhD outputs. That is a very important part of the PhD, is that the PhD is not the only output of a thesis, but to bring the publication effort forward. And I think these PhDs, all the PhDs that have been submitted have achieved this high mark, and we are very proud of all our students, and so we are confident about the ideal future, because these students, okay, they are smarter than us and we are improving. It's no doubt of that. So the next one, I will present the 3 prizes that we have given this year. If you can pass the next one. So the first, and this is alphabetic order, so they are in the same level, are the prizes. One is for Andrea Ribeiro with a thesis called Development of an Agriculture Drought Risk Model for the Iberian Peninsula. Then the other one is for Felipe Luz with multi-element and isotopic geochemistry and metapolites from the volcanic sedimentary complex, Iberian Pirate Belt, Portugal. And the last one, Rodrigo Amaro e Silva, with spatial temporal soil forecasting. So I'm very proud to give these awards to these 3 PhD. Okay, they are not anymore PhD students. They will be forever students, I hope. But this is the moment that the presential room will be much better. But I would like to give an applause to these 3 fellows. Okay, we can share this by Zoom, but giving an applause to them all. Okay. So thank you very much all for being here and for sharing with us these brilliant new PhDs at IDL and elsewhere, because we are not only thinking on the IDL, but on the scientific community in Portugal and elsewhere. Thank you very much for your effort, and we are proud of you. Thank you.
I think we have a few minutes if anyone wishes to say anything, especially the winners.
Yes.
Not particularly to thank, but just share some ideas.
Okay, I just would like to thank all the ones that support my work and all the companies that allow me to develop this work and learn with them. And I really like to mention all the economic geologist masters, because they play a really important role in my PhD path, with all the helping in the lab work, brainstormings, and even in the beer time. It was really important. And last but not least, the Earth System doctoral program. I'm really proud to share the prize with one of my colleagues, Andrea. You used to say that we will change the world in some way, so it's really good to be here with her and with my panel solar guy. So congrats for you too. And in the end, thanks to IDL, because with this multidisciplinary program, it was really nice to develop a lot of skills and learn a lot of things. Thank you.
Thank you very much.
I would like to give the floor to Rodrigo to the end, because Rodrigo was a representative of the PhD students for a long time, and he played a big role in this Earth Systems doctoral program. And first, I would like to congratulate him and Felipe as well. And thank you very much for IDL for this recognition. And in particular, I would like to thank and acknowledge my PhD supervisors, Ana Russo and Célia Gouveia, which we still collaborate, and they are supportive every time in every moment. Also to acknowledge the co-authors of the papers I produced during PhD, Carlos Pires, Patrícia Páscoa, and Jacob Zeichler. And I also would like to thank Carlos da Câmara and Ricardo Trigo, which were the external advisors of this thesis, and they followed the steps very closely during all the time. I would like to felicitate as well IDL for the high quality of the research that was presenting during these 2 mornings.
and felicitate for these initiatives of the IDL conference and these awards, the travel awards and the prize awards, which really help to encourage and support the early careers. And if we are working together towards an international recognition, it is important to value ourselves first in our home institution.
So I guess it's my turn now. So I'm only going to thank IDL because everyone else was already acknowledged on my PhD thesis. And it's a double appreciation or thank you because we're here for the prize, but also the Earth Systems program itself was devised and promoted by IDL. And by chance or not, all the winners are from the Earth Systems PhD program. And lastly, a word to all the other PhDs. I can assure you that all these 3 winners had a moment in their PhD, shorter or longer, where they felt like, I'll just say bad, to not say a not so good word. They all felt bad at some point in their PhD. Confidence goes up, confidence goes down, and then hopefully it goes up again. And with effort, contact with your supervisors and your friends and your colleagues, everyone can finish their PhD at some point. And I'll close from here.
Thank you all for your words. Well, what can I say? We are nearing the end of the annual conference. Well, not nearing the end, but at least for the IDL participations. I think our speaker is already online, although we are still 3 minutes in advance, which is probably a record. I don't know if anyone wishes to say anything more, just to fill in a bit of the gap, just so that people that haven't been accompanying the whole morning, they can join us at noon and still hear the beginning of the presentation.
Yes, I can say something. I think that what this PhD refers, it's very important. It's to see the other examples, and the new PhD also feel that they can follow some raw examples and can ask for help in some less good moments, like Rodrigo says. Not every moment is a glorious moment with prizes and honors, but some steps are more difficult, and we have to make some efforts that sometimes we don't see the finish line. Sometimes the finish line seems very far away. But when we look at these examples, it's easier to find this raw model. And I think it's very important that all PhD students feel that they are in a group that can help each other. It's very important not to be alone and to be in a group. In this sense of group, I think it's very useful for all PhDs. So that's the important thing in the IDL PhD program, is that we can share also our glory and obvious our problems. That's the most important thing, I think.
Thank you.
So get inspired on these role models, okay?
And ask for help wherever you can find it. I think it's an excellent advice.
Research generation, okay?
Anyone else wishes to share some ideas?
Lots of moments are not glorious, but the glorious moments compensate the others. Huh? Don't forget, It's a lot of bad moments, but then the glorious, it's very nice. Eh? You can look at their smiley faces, and all the PhD aim to be like that. Eh?
Yeah.
That's the very important thing. Capture this moment. Eh?
It's all worth it. Yeah, definitely.
Screenshot can say, okay, see, they are smiling.
Yeah.
Everyone is smiling.
Even a PhD student. Eh?
Okay, so I think I will now hand it over to João Duarte to present our speaker, our invited speaker, because he will do a much better job than I could do. So go ahead.
Okay, can you hear me?
Yep.
Okay, so first of all, thank you, and most importantly, thank Michael for accepting this challenge of being with us. It is great to see you, to have you here with us, not physically. We had like a plan to meet in Lisbon, but that was not possible this year. Maybe later in the year. I was talking with Matthias, maybe later. So everyone will be invited here. So what can I say about Michael? Michael is a physical scientist at NASA. He did this little bit of background. He did his PhD in '98 in the University of Missouri in St. Louis in observational cosmology. He worked since in many different things, from machine learning, history of astronomy, exoplanets, and planet habitability. He recently ended over in a new, I don't know, great big adventure of trying to reconstruct the whole climate history of Venus. And he has developed, is one of the developers of a model, an numerical model that is Rocket 3D, that has been using to model the atmospheres of other planets and exoplanets. We started to collaborate via Matthias Green and Dana Davis, which was a student in IDL at Earth Systems, on the climate of the future Earth. And he will tell you why we are doing that. But we also have plans to work on the climate of the past Earth. And we have just got a grant to investigate the climate of Archean, and we are very excited for that. So welcome, Michael. You are really invited to come here to Lisbon. We have this plan to organize a meeting of our informal group in Lisbon, which is normally open to everyone that wants to participate. So we are very much looking forward for your talk and that everyone meet you. Thank you again.
Great, thank you, João. Can you all hear me okay? Okay, nodding.
Yes.
Okay, so let's see if I can share my screen here. Take me a minute to get things organized. Let's see if that will work. I have to bring up the right presentation, sorry. Strange, always something funny happens when you want things to work. Okay, let's see here. Let's get a little bit more, sorry. Zoom always wants to do things its way, not the way you want to do it. Okay. So hopefully you all can see that now. So this is a project that I've been doing. Actually, it ended up being a couple years now with João and Hannah Davies and Matthias Green, which is apparently some of you know him as well over at Bangor Oceanography. And it all came about because Matthias and I have been working on some Venus related things for a few years. And we were at, I think it was EGU a few years ago. And I met João and Hannah, and they had a really cool poster about the future Earth. And by future, João says future, but he means deep future, hundreds of millions of years into the future, not tens or hundreds of years, as we are very concerned about in terms of climate change studies. And we decided that we would try to work together and see what the climate of this future world would look like. And I think some very interesting things came out of this study that I want to share with you. And I think they have implications for a lot of exoplanet research that my group is involved in particular. And most of my group is located in New York City. We have a small satellite office of Goddard Space Flight Center located in New York City in Manhattan, which is called the Goddard Institute for Space Studies. And most of the people there, there's about 110 of us, are doing climate change studies with a general circulation model. But my subgroup, which is about 10 people, we've taken that Earth system model, as we would call it, and have expanded its capabilities to do other kinds of planetary atmospheres. So everything from very ancient Earth, ancient Mars, modern Mars, ancient Venus, and a variety of exoplanets. And we keep expanding its capabilities as we go forward in time. So I'll show you some results from using that model to this project that we have together. So in this particular study, we modeled 2 future supercontinents, as they call it. There are more in this paper that Hanna led with Matthias and Joao in Global and Planetary Change, as you can see here in the journal. And I love the title, I'm sure many of you would too, Back to the Future, Testing Different Scenarios for the Next Supercontinent Gathering. And we looked at two of the different scenarios that Hanna put together. One is something called Orica, which is an equatorial supercontinent, and you'll see what I mean by that, which is about 250 million years into the future. And the other one is called Amazia, which is a polar supercontinent, which is about 200 million years in the future. And I'll try to keep the color schemes right. So when I'm talking about Orica, I'll generally keep things in red, and Amazia, I'll keep them in blue. And I will also talk about modern day Earth and some changes we've made to that to make comparisons a little more intuitive, hopefully, when we move forward in time. So these are some slides that I modified that Hanna gave me. So thanks again to Hanna for sharing these slides with me. So this is Orica, the equatorial supercontinent. You can kind of see how things move in time. As I remember correctly, this hypothesis is that there will be a rift in Asia and that the Pacific and the Atlantic would close. And by doing so, you end up with the scenario in the lower right here, which is this low latitude supercontinent called Orica. And you can see all the little pieces of the puzzle that I'm sure all of you are much more familiar with me. I'm really a climate scientist. I'm not a geophysicist or geodynamicist of any sort. So that's our Orica scenario. Again, very low latitude. We have polar oceans, and it'll be quite interesting to see what the climate looks like, at least our initial studies. The other one is called Amazia, the polar supercontinent. And in this case, as I understand it, supercontinents tend to like to form 90 degrees from the previous supercontinent. So since the previous supercontinent, this Pangaea supercontinent, was also sort of low latitude, I guess, the rift would tend to be, as you see here, broken up where the northern, well, basically most of the continents as we understand them, South and North American continents, and Africa and also the Asian and Australian subcontinent would move north into this sort of supercontinent you see down here in the lower right, and Antarctica would stay where it is. So you end up with a scenario that looks sort of like this. So Antarctica doesn't change too much from present day, but you end up with the supercontinent. And what's interesting about this, I just pointed out for you to keep in mind as we move forward in the talk, is that there's no polar ocean as we have today on Earth. So everything's locked up in the northern hemisphere in the same way that Antarctica covers the South Pole in the southern hemisphere. And again, that will have some important consequences for our study. Now, we had to do some other things for this study. We had to pick what kind of topography we wanted, of course. You can't just run the scenarios. Now, I should say, I think when paleoclimate, deep paleo time studies were first done, of course, they had discussions about what these topographies might be like in the past, because we have very little information when we go too far back in time, as you might imagine. So people often just did flat continents and things of that nature. So I shouldn't say we, I should say Hanna and Joao and Matthias came up with 3 different scenarios for what the topography of these worlds might be like, which again will play an important role, at least in one scenario, for the climate of this system. So one is a low mean topography, as you can see here, where, as we say, land is close to the sea level. There's no mountain chains We call this our control run. So our topographic height, as I say here, will be randomly selected for each grid cell between 1 to 200 meters for these two scenarios. So this we call control, CTRL. Then we have one with a higher mean topography, what we call present day, which is a bit more like present day topography, where it ranges between 1 to 4,000 meters, again, with no mountains. So this is PD. So we have control, PD, present day, and then there's one more, which we call mountains. And so we take that first scenario, the control scenario, and we add mountain chains to those. And you can see those mountain chains showing up in the topographic relief. So there's some mountain change in Antarctica. You can see in the one on the right, you can see the remnant of Africa, and also, of course, Arabia, where you can see some mountain chains there. And of course, in Orica also we have some mountain change. And those, again, we'll see towards the end that interesting things happen in this particular scenario, which is sort of interesting. Okay, so let me just say a little bit about the model. I'm going to try to stay away from too many technical details, but I just want to give you some background. So this particular version of the model is fairly low resolution. It's only 4 by 5 degrees. Modern Earth climate models are something like 1 by 1 degree these days, or smaller. That's on a latitude longitude grid. We use a 40-layer atmosphere for those that are interested in such things, and we use a fully coupled dynamic ocean with 13 layers. We use the same orbital obliquity and eccentricity as modern day Earth. But for these future time scenarios, we change the rotation rates. So we have done some scenarios, as I'll show you, for Earth at 24 hours to make comparisons, but these Orica and Amazia scenarios will be at 24.5 hour long days. So Matthias, who has done a lot of tidal dissipation studies, did the calculations, and he estimated it would be something about a half-hour longer length of day, roughly 250 million years into the future. We can't know exactly because the tidal dissipation is the main factor here, the oceanic dissipation, and as you all know, as the planet evolves forward in time, how the tides will be set up in the future is a big unknown. And again, to keep things simple, we don't have any plants, because we don't know what kind of plants there might be on this Earth in 200 million years. Maybe we'll do such a great job of destroying the planet, there'll be nothing left, but let's hope not. We pick a standard ground albedo of 0.2 at model start, and we pick a 50-50 clay sand soil mix. So you're probably asking, why does he pick these values? They're actually kind of becoming the standard values to pick for exoplanet studies. So I thought it'd be good if we tied to that community a little bit tightly. As for the atmosphere, again, we're not sure what the future atmosphere will be like. But we've just picked a 1-bar atmosphere, a modern pre-industrial atmosphere with a bit of CO2, 285, and less than a part per million of CH4. So not too much greenhouse gas, but what we would have had about 150 or so years ago. And then for the insolation, how much incident radiation does the planet receive? So for that, there are people who have done solar evolution studies. In particular, Mark Clare is the one who's done the most detailed calculations in recent years. And you can get tables from him that tell you what the insolation would have been like going forward in time, and of course backward in time too. For those of us doing paleoclimate studies, we use Mark's work to figure out, exactly what the sun's luminosity would have been, say, 4 billion years ago, when it would have been 30% less luminous than it is today, which is related to something you probably all heard of called the faint-young sun paradox. But regardless, for Orica, as you can see here, those estimates are that it's about 2.5% brighter, the sun. So instead of 1361 watts per meter squared, which is what Earth receives today, it receives about 1396. And for Amazia, which is not quite as far in time, again, it's about 2.2% more, 1391. I mean, those numbers don't mean much, but you'll see what kind of effect they have when I show you. And then to tease apart the differences in rotation rate and the insolation, I just took a modern day Earth type simulation. I changed its rotation rate for a set of simulations, and then I added the insolation similar to the Orica simulation to tease out what kind of effect insolation would do. It just means I decrease the number of simulations I do, just doing 2 more instead of doing 4 more, because these simulations take well, thousands of model years and a few months to run each of them. So it's quite time consuming. And as you'll see, I had to already do quite a number of additional simulations to make these things as realistic as possible. Okay, so we go forward. This is what our simulation setup looks like. I'll try to keep away from using the simulation numbers, but you'll see them turn up now and again. But the first 3 simulations, again, are going to be these Orica simulations, 250 million years in the future, with this low latitude supercontinent, where we have this control run, 0 to 2 or 1 to 200 meters high topographic height, the present day, which is a bit higher, and then these mountain chains added to the control run. And you can see again what the insolation is, again about 2.6% more than present day. Length of day, 24.5 hours, and then runtime is not so interesting for you all, but just so you know, that's how long we ran the model to come into what we would call equilibrium. And in terms of the hydrological cycle, that's what takes the longest time when you change topography. It takes a while for the rivers and the lakes to come into equilibrium. And we like to be in equilibrium so we know that things aren't changing radically anytime soon. And then the same for Amazia, 200 million years into the future. Again, we have 3 different scenarios. And again, same length of day, slightly less insolation, it won't make much difference. And then to tease out the differences, as I said, between the rotation rate and the insolation, we did 3 more simulations of taking modern day Earth, but using the same albedo, by the way, and soil as the Orica and Amazia simulations, just to get a baseline, and then changing each of these things separately. So one where we added the extra 30 minutes to the length of day in simulation 8, and then in simulation 9, increase in the insolation. Okay, hope you're all with me so far. Let's move on to what they look like. So, so Hannah gave me extremely high resolution versions of her model. I had to downsample those, and I downsample them by elevation under my 4x5 lat long grid. And when you do that, based on elevation, so I take, say, 20 grid cells, I look at what the mean height of those 20 grid cells is, and I decide if it's going to be a land grid cell, meaning positive altitude, or a lake or a ocean grid cell, which means negative. And that's why you can see in the Orica, the 3 Orica simulations, that the distribution of the land is more or less the same, but the lakes and the edges are slightly different in the 3 simulations because of the way we've done that. And just for fun, I've overplotted what the present day continental outlines look like. So those are the 3 at the top, the low latitude Orica. And then at the bottom, you can see the same kind of thing happening, not quite as drastic, where when we do the subsampling, things look a little bit different. You can see a bit more high latitude lakes, if you can see that in the plots, hopefully, in simulation 4 and simulation 6, these Amazia control and the mountain runs, versus this present day run. Not too surprising, because the present day run has these higher mean elevation, as you might expect. So just to show you what those look like. So this is just a longitudinal average of the topographic height, and then a latitudinal area weighting as we go down, because the latitude longitude grid cells are smaller at the top than they are at the high latitudes versus the low latitudes. And you can see here that the height is, as I say, well below 100 meters, the mean height for this particular world. And you can get 0 in the part where there's no land. So it's just the topographic height of the land in this sense. So that's our control run for Amazia. If we look at the present day control run for Amazia, again, this is our high latitude supercontinent. You can see that the mean is much higher, as we said it would be. And I just overplot modern day Earth's topography in the same, that's put together in the same way. You can see it's not that different from modern day Earth. So it does mimic it. Of course, not in Antarctica quite, because of course we have ice sheets in Antarctica, which we'll come back to in a moment, which play an important role. And then if we look at the mountains version, again, you have this low topographic height, but the mountains do play a role, of course, also in what the mean topographic height is for a given latitude band. So you can see what that looks like there. All right, and then here they are all put together, just so you can kind of see them for comparison purposes. The low latitude, the one with this present day sort of altitude for the topography, and then this one with the mountains on it. Okay, but not so fast, as I've kind of said. There are some possibilities for ice sheet growth in these simulations, and actually these not only may, but will seriously affect the climate in some cases. So we have to examine how we might take that into account. And this is something that you learn from doing climate simulations for many, many years, how this might be addressed. So what I'm going to show you are, again, those 3 Amazia simulations, because those are the ones where it really matters, these ice sheet growths. For the low latitude Orica simulations, we don't have any ice sheet growth because it's at low enough latitudes that ice really cannot grow on these in any kind of way that's important. So what we've done here, for example, in the control run is I've let the simulation run for a few thousand years and let snow and ice build up at these high latitudes. And this, for example, is the December, January, February. It's a 50-year climatological mean of those 3 months. So we can get an idea of what the ice sheet buildup looks like. And what we did to address these ice sheet business is that we took the summer months for each of these. So in this case, I would look at how much ice built up in Antarctica in this case, because it's summer months there. So I would know that would be the sort of the minimum extent of the ice rather than using the full winter extent, because in our model, once I set the ice sheets in place, they cannot move. So I have to decide, okay, this is where my ice sheets are going to go, and these are going to be the heights of my ice sheets. So we do that for each of the simulations. We take these 50-year climatological means from December, January, February for the Southern Hemisphere, and then January, February, March for the Northern Hemisphere. And we use those to figure out what our ice sheets look like. And you can see here, this is for the control run. You can see for the present day where I have higher mean topography, that there's a lot more snow and ice. This is just the snow and ice coverage, just the fraction. I'm not showing you the actual altitudes. I'll show you that in a moment. And then again, for the mountains, you can see there's much less going on. A lot of it actually ends up on the mountain chains themselves, as one might expect. Okay, so I'm sorry, this is a little bit, hopefully it's not too hard to see. But what you can see here on the left are what we started out with from Hannah's downsampled simulations and what those topographies look like. I'm going to show you one of them in detail in a second. And then on the right, we look at what the ice sheet's growth looks like and how we added that. So basically we add that topography to the simulations so that they're more correct for what they should be. So in the upper right, you can see the Amazia in the red dotted line are where the ice sheets were added from those 50-year climatological means. And you can see it looks important. There's, we've added almost 800 meters worth on each of those. The one in the middle, I'm going to show you a bigger blow-up version of that in a second. But again, you have this mean climatological height, and you have this red line, which is where the ice sheets are. And I overplotted, and again, I'll show you in just a second, what the last glacial maximum looked like. And then at the bottom, the Amazia Mountains, where actually nothing really changed. So not a lot of ice sheet growth on those mountain chains, it turns out. Okay, so let's look at this Amazia present day, which is the more interesting of the 3. So first of all, again, this dark blue is the topography that I got from Hannah and João. And the red dotted line is what the topography change was with the addition of those ice sheets that I added to the model. And you can see it's quite distinct. Again, adding several hundred meters in some cases, and in the Antarctica case, several thousand meters. Now you're probably asking, why do I bother putting the last glacial maximum? So one thing I should mention is that our model does not, like I think any other GCM, all other GCMs, do not have active ice sheet models in them. Most of them do not have that. You usually have to do an offline sort of calculation, but not being able to do that, we have to kind of hack things in a way. So we let the model march forward in time. As I said, we look at what the ice growth looks like, and then we do some longitudinal averaging to simulate kind of the ice sheet movement in time, kind of smoothing out things. And I think that this is kind of encouraging, what I'm showing you here, because certainly the last glacial maximum is a good barometer for what we know the planet looked like. And you can see that at least in the Northern Hemisphere, it's not too different. I mean, of course, at lower latitudes, we don't have quite the same, but the topography is quite different. So we don't expect it to be exactly the same, but at really high latitudes, it looks quite similar. I think that that's pretty good. And then again, in the Southern Hemisphere, it's remarkable how close our ice sheets look to the last glacial maximum ice extent and height. And Antarctica, I thought that was really quite remarkable. So I felt kind of good about our choice in terms of the ice sheet growths. Okay, so that's kind of where we are, at least with this polar supercontinent scenario. Now, the next question is, why do we see so much snow and ice deposition at these high latitudes compared to modern day Earth or Orica in this Amazia simulation? So you can see here, these plots are what the ocean circulation, as I said, it's a fully coupled, fully dynamic ocean that we use, which is quite nice in a scenario like this. And you can see what the ocean currents look like here. And as one might expect for that Amazia present day, you have no northern polar ocean at all. So you have no way to transport heat from the ocean up to those high latitudes. All you can use is the atmosphere, in essence. Whereas if you look at the Orica simulation in the upper right, you have a very nice polar ocean there. You have a lot of heat transport. Nothing gets frozen up there. And in modern day Earth, we know, of course, more and more that, of course, the northern polar ocean is melting in the summer months more and more. And we see the same in our simulations. And of course, the ice sheet itself over the North Polar cap of Earth is not terribly thick, as many of you know. It's not like we have thousands of meters high mountains as we do in Antarctica. Okay, so let's investigate what happens when we change the rotation rate by 30 minutes. We make the day length a little bit longer. So here on the left is what you see. This is a figure I took from Wikipedia, which is based on an old NASA graphic. You can see that there are these circulation cells, which everybody knows as the Hadley cells. And there are actually 3 cells. They have different names, but here they just call them the lower latitudes ones. They call the Hadley cell. Then there's a mid-latitude cell and a polar cell. And those are designed, the way they come about is because the Earth is spinning quite rapidly, and there's a Coriolis force, and that breaks up the general circulation from the equator to the pole. Whereas if you look at this kind of primitive diagram on the right, this is an example of what Venus's Hadley cells look like. Venus is an extremely slowly rotating world. It has a length of day. Its solar day is about 117 times longer than Earth's solar day, and its sidereal day, for those of you that care about such things, is about 243 Earth days long. And of course, it also spins the opposite direction, but again, extremely slowly. And what we see on Venus is that you have these very large Hadley cells, just one in each hemisphere. That's it. And therefore, they're very efficient at transporting heat from the poles to the equator. And the temperature differential between the poles and the equator are quite modest in comparison to Earth, where the breakup of these cells, because of its rotation rate, play a role. So that's something we want to look at. If we slow the planet down some, do we see a difference in the temperature contrasts on the planet? So that's what I'm showing you here. This is from some work by Adam Schoeman, who unfortunately passed away earlier this year. It was a great loss to the community. He was a University of Arizona professor. This is a plot that I've modified a bit from some work of his from 2016 at the Comparative Climatology of Terrestrial Planets 2 conference. And what you see here are some simulations where he's looking at the temperature differences between the different latitudes. So it's a mean of the temperature at latitude 0, so at the equator, all the way up to the poles. And you can see that when the day length is very short, say a 3-hour long day, so the planet's spinning around one time every 3 hours, that the temperature contrast between the pole and the equator is quite large. And as you slow the planet down to say a day length that's twice as long as Earth's present day length, 48-hour long day, you can see those temperature contrasts are much more muted between the pole. And that is again related to the size of these Hadley cells changing as we slow the planet's rotation rate down. So the next question is, of course, do we see anything like that? And I'm pleased or unpleased, I'm not sure which, to report that no, we see almost no difference, which is kind of interesting. No one's really looked that I could find, at least in a study, of what kind of effect such a small rotation rate difference would have. And this is actually what the rotation rate difference, temperature difference would be between the equator and the poles for the Earth simulation. So in this case, I took this kind of pseudo Earth simulation. I just changed its rotation rate, and then I compare what the temperature difference is between the pole and the equator, and you can see that they're almost exactly the same. They're within, you know, maybe a degree of each other. So there's no real difference here. Another thing we can look at is something called the stream function. That tells us what the strength of the Hadley circulation is. And if you look at just the strength in the tropics, so those would be this bright red and bright blue cells that you can see here, the ascending and descending cells in the tropics. At the top is the modern day type Earth scenario, and the bottom is the one where I've just changed the rotation rate. You could look at the data min and data max, but it doesn't matter. But the point is, it's less than 1% difference basically in their strengths. So that half-hour day length difference doesn't seem to make a big difference in this sense. Although I should just add that it's rather interesting. If I just take the surface temperature from one versus the other, oops, looks like I skipped over one of my simulations by accident. If I just take the simulation of the Earth subtracted from this one with a different rotation rate, I do see some changes, especially in the Northern Hemisphere, of up as almost as much as 5 degrees. But the mean, as you can see down here in the lower right, is showing us that the global temperature changes is very, very modest. So in general, I think we came to the conclusion that at least for these very deep future time scenarios, the rotation rate's not going to play a big role in the climate. What's really going to play the role is going to be the insolation, and of course, the way the continents are laid out. So if you look here, here's the difference between what we call simulation 9 and 8. So this is the Earth simulation with the Orica and Amazia rotation rate, but with that larger insolation. That's what simulation 9 is. So if I take the one with the higher insolation minus the one with the lower insolation, you can see now in the lower right, you can see that the mean surface temperature difference between these two simulations is almost 4.5 degrees. So that doesn't surprise any of us, of course. If you increase the insolation by a few percent, you should expect the surface temperature to go up, just as we add CO2 more and more to our modern Earth atmosphere, the temperature is going to go up. That's just the nature of the beast in a sense. So, but although we do see some, again, extreme temperature differences, again, more towards the northern polar regions where you have as much as 16 degrees temperature differences. So it's not, we can always look at global means, but it's also important to look at some of these min and max. The min doesn't change too much, but our maximum surface temperature is certainly changing quite drastically. Okay, so what in the end do these simulations look like? So let's focus on these modern Earth simulations just to start. So first of all, if we just look at the mean surface temperature, that's this T column, the pseudo-modern Earth is about 13.5 degrees for its mean surface temperature. And if you change the rotation rate, it only changes by 0.2, as we saw that earlier when we subtracted the two. And when we go towards the one with the higher insolation, you can see a drastic change again, as we saw a little bit, almost 4.5 degrees difference. Some of those changes are noticeable in this column called the snow fraction, which I've also showed you. And you can see here that the snow fraction, as one might expect, this is the global snow fraction, the percentage, has decreased by almost 3% from the simulation that we started out with for modern Earth. And just increasing the insolation, it drops by almost 3%. Again, not too unexpected for us. Okay, and that's just what those three simulations look like, just for fun. You can't see huge differences, except you can see the big difference between, I mean, some big differences between simulation 9, which is the one that's hotter with the higher insolation, versus the two up top, which just changed by the rotation rate. You can see that just a little bit less cool at higher latitudes. Okay, so let's move on to Orica. That's our low latitude supercontinent, where we have these polar oceans that are open. And here, I find it remarkable that, as you can see, the mean surface temperature for all three of these, no matter what the topography is almost exactly the same, within 0.1 degree. It's really quite remarkable. There's a little bit of snow that shows up in the most northern piece, or not most northern part, on the mountains themselves, on the mountain chains themselves, which I'll show you in the next plot, which is where that comes from. So if you look here, you can see, my slide didn't turn out so well, but you can see, for example, that the data min in the first two are very similar. They're like minus 4.6, minus 2.9. That's the lowest surface temperature value. And if you look at the data min for the one at the bottom with those mountain chains, it's much lower. It's minus 18.6, but that's because you have these very high altitude mountain chains there. And that gives you these much colder temperatures. So you can see that the way I've done these temperature maps is that if it's blue, it's below freezing. And if it's, you know, orange or yellow, it's above freezing. So you can see on those mountain chains that we see a lot of temperatures below freezing. So we, of course, get these interesting temperatures. But as a whole, they're a very, very small fraction of the total area of the planet. So the mean surface temperature doesn't change by very much in this case. So I thought that's kind of interesting. So topography is important, and in this case, in a local scale, but not so much in a global sense. It doesn't change very much. Okay. Now let's look at this Amazia, which I think is one of the more interesting ones. And here we see something quite interesting. So the mean surface temperatures for two of the simulations are within, as you see, about 0.7 degrees, 19.5 and 20.2 for the control run and the mountain run. So again, the mountain run is just the control run, but with just these little mountain chains. So again, that kind of jives with what we just saw, that the mean global mean surface temperature is not changing a lot. But if you look at the present day, the one with the higher topographic height, you can see it's much cooler. It's several degrees cooler, 16.9 degrees in the global mean, which is quite surprising. And that ties back into the snow fraction, as you can see here on the right, where that simulation 5 has over 10% of snow coverage, whereas the other two are more around 5%. What's interesting, I think, also is that present day simulation number 5, 10.2, has larger snow coverage than either of those, any of those Earth simulations, modern day Earth simulations. That's kind of interesting. So you've given the planet a few percent higher solar incident radiation on the planet, yet its snow fraction is higher, even if its global temperature is still about 3 or 3.5 degrees higher than Earth. Not unexpected given the insolation, but yet still has a lot of snow fraction. And again, that goes back to this issue with the high latitude supercontinents. Okay, so now what do those look like? So these are the pictures of the surface temperature for these worlds. It's hard to see a lot what's going on here, but if you look at the one on the upper left and the one on the upper right, the one on the upper right is that present day one with the higher topographies, and you can clearly see there's a lot more dark blue at those high latitudes, again, because the planet's topography is higher there. Basically what's happening, the difference between these kind of scenarios is that something called the lapse rate is different between these scenarios because of the altitude. And instead of you getting rain, for example, in the summer months at these high altitudes, at high latitudes, you're getting snow, basically. So you're precipitating snow, not water. And of course, in the bottom one, again, you see surface temperatures in general very similar to those on the upper left. But again, on the mountain chains, again, it's very interesting. You see a lot of snow precipitation on the mountain chains, again, as one would expect and as we saw in that Orica simulation earlier on. Okay, and these are just all of them put next to each other. I'm not sure that it's hard to to really distinguish what's going on here, but in essence, again, you can kind of see in the column on the left, the Orica simulations, where the first two are very similar, but the ones with the mountain chains really do look quite distinct. And just to go back to something I wanted to show you in this particular table, there's another metric that we do that people tend to use in the exoplanet community called the habitability fraction. So it's kind of a silly metric, but it does tell you some things. It more or less confirms your preconceived biases, I would say, in a sense. So that's the column on the right there. So there's two different values given there. The traditional way that this habitability fraction is used is that you look at the planet and you figure out what percentage of the planet has surface temperatures between 0 degrees centigrade and 100 degrees centigrade. So in all of these simulations, we don't have any surface temperatures near 100 degrees centigrade. It's really the colder temperatures that are going to determine the fraction. So if we just look at the Orica simulations, again, I think things look kind of like you would expect, at least in that sense. So for the first one, we don't have any surface temperatures really below 0, and so our habitability fraction is 1. If we look at the present day one, it's slightly less because we do have some instances where we have a little bit of temperature below freezing. And then in the mountains, it's a few % lower, again, because of these mountain chains where things are below freezing. Now, the number on the left, I said, is the 0 to 100. The number on the right is a bit more, it's a bit expanded. It goes down to, I think it's -18 and up to 120. Again, the higher end doesn't matter because, of course, we found life forms on Earth, as many of you know, in quite cold climates. So it doesn't have to be 0. And that's why those numbers are a little bit larger. The habitability fraction is larger in those sense. And as you look down through here, you see that the simulation with the lowest habitability fraction is, of course, that simulation 5, that Amazia PD, where we have those large areas where things are quite cool. It isn't even a smaller value than present day Earth, which I think, again, is quite surprising in a way. And then, of course, for the Earth simulations, things kind of move in this way you expect. There's not too much difference between the two with the different rotation rates. But as we increase the insolation, we're, of course, decreasing the lower surface temperature possibilities from the earlier simulations. And of course, we get a higher surface fraction of the planet in this kind of habitability metric. As I said, often used in the exoplanet realm. Okay, and again, if we look at those Amazia simulations in the middle, again, you see these high latitude regions where you have quite large amounts of cold weather. And on the right, of course, there's those Earth simulations where we change the rotation rate and the insolation. So that's about all I have to say. Just to kind of summarize, I mean, for the Orica simulations, we're seeing, again, these mean surface temperatures are all very similar, all within 0.1. And they are, in general, the warmest simulations that we see. Again, not surprising, because we have very little snow and ice going on here. Again, only in the mountain simulations at the very top. And we don't have, we have these open polar oceans. So we have plenty of ocean heat transport to the high latitudes to keep ice from sticking around up there. The Amazia simulation, which again, I think is one of the more interesting ones, we have quite a large span in mean surface temperatures, which I think probably we wouldn't have predicted from the start, just based on the topography. Where the low surface temperatures are really due to these large ice sheets that build up at high latitudes. As I said, the oceans cannot transport heat to these high northern latitudes because there's these continents in a way. And again, the higher elevations for that present day simulation really are playing a key role. And one thing I haven't even mentioned yet is that there are large amounts of water trapped in these polar caps, as you might imagine, as we see actually on our neighbor Mars. That's where most of its water is locked up, is in its polar caps. And that the global equivalent layer of water on this PD simulation actually dropped by 50 meters. Now, we don't see a difference in the topography from that because we're using a bathtub type ocean, but nonetheless, the water level is dropping, as we know from the Lynch glacial maximum, where a lot of water was trapped in the high latitude regions. The water levels the ocean levels on Earth, of course, drop. So that again is in line with what we've seen in Earth's past. So again, to recap for this Earth simulations, just to remind you that this difference in rotation rate is only changing things, I mean, by 0.2 degrees. But as I said, locally, there's some larger changes, but in general, it's a very small effect. And the insolation increase is where things really matter. We get almost a 4.5 degree difference in temperature. So for future work, well, we're hoping to write a much longer. This is a paper that was just resubmitted to GRL recently after replying to some referee reports, which were quite useful. But Joao and Hannah have some other reconstructions that we will look at going into the future. We're working on implementing an ice sheet model into the Earth climate model, and eventually we'll get that on the planetary side of the house. And maybe we'll even try to do some offline ice sheet modeling if we can find the time to do that a little bit better. And really, we need to look closer at the examination of the sea fall level and what its implications might be for the planet. So that's all I have to say. So thank you so much.
Thank you very much, Michael. That was such an interesting presentation. I will open the floor for some questions. please.
Yeah.
Go ahead, Rita.
I'm Rita Carvalho. I'm working with climate models, and I'm mostly interested now in the influence of vegetation on climate. As you may know, that changes in vegetation has been responsible for changes in climate for as strong as climate change. So I was wondering, what if you put some vegetation in your continents, like in your Amazia, in the Orica simulation, you could put tropical vegetation and see what happens. And even in the Amazia simulation, if you put tundra-like vegetation, then you probably reduce the amount of snow and ice. And that could have serious implications to the climate. Would you be interested in looking at that?
You're absolutely right, Rita. All of those things would have large influences. I mean, I'm not so sure about the Orica if we want to put tropical vegetation in, because if I remember correctly, the last low latitude supercontinent on Earth had a lot of dried out areas in the interior. So we would probably want to consider putting such vegetation more towards the edges. And then you have to decide what kind of percentages you want. I guess you could look at precipitation output from the model and decide, okay, well, if it has this kind of precipitation pattern, then this kind of grassland or tropical leaf cover could be put there. And that's something we could do down the long run, absolutely. So I'm not sure how much effect it would have on the global sense, because again, in the centers, probably it will make not so much different. But in the Amazia simulation, as you point out, it could have a much larger effect where we put those things. And again, we would have to look at how, what the precipitation is telling us in a sense, because it's hard to know, what are the soils going to be like 200 million years in the future. We know what the wind patterns will be like, and we know what the precipitation will be like. And one thing the model does have in it is that the albedo of the soil does change as it gets wet or is dry in that sense. But without any kind of land plants, of course, everything can be quite different, as you know. And we actually have a group at my institute that does look we have a vegetation model at my institute, and we've been talking about applying that to exoplanet simulations. But the lead person that has been trying to think about different kinds of plant functional types that we might utilize, and she just hasn't made that much progress on it. But it's a really good point, Rita. It's something that we're definitely interested in looking at.
Hi, can I raise a question? Ricardo here.
Sure.
Of course, it all depends a lot on the Milankovitch cycles, and in the past, we noticed that even without the human contribution, the climate of the Earth has been bistable. So in the last 1 million years, depending on the insulation factors, eccentricity, obliquity, everything. So I was wondering, are you expecting, if you are able to run your models for thousands and thousands of years, to obtain bistable climates?
Well, it's something that we haven't done, so I don't know for sure. We have done different simulations with different kinds of spin orbit combinations and different kinds of eccentricities, but haven't looked at it in detail. Part of that is because it just takes a long time. I mean, to get those kinds of simulations running, as you know, it can take 10,000 years to come into some kind of equilibrium. And that's typically the limit that we run the model, just because it takes 6 months, even at low resolution, for it to run. If we wanted to run high resolution like the Earth side of the house does, you're talking about, it could be as long as a year or two for your simulation to come into equilibrium. So it's more a question of not that we're not interested in it, but just a practicality issue. But you're right. And one of the things I didn't mention, which I'm glad you brought that up, the Lace glacial maximum is a Milankovitch cycle type event. So it's exactly the case where, the orbital parameters change a little bit and the planet goes into this, this completely different climate state. So
and where, for example, CO2 was much lower. So CO2 has been varying dramatically, just naturally.
Yeah, well, one thing I meant to put here in the future work was we were asked about by the referee to mention something about the carbon cycle, and certainly that's another thing we can look at looking at differences and how much CO2 is in the atmosphere. Of course, the CO2 drawdown can be quite distinct depending on what your surface is, right? What's the weathering rate on the planet? And I think just now people are, at least on the exoplanet side of the house, are getting more interested in how weathering rates vary between different kinds of worlds. Basically, I mean, there's these ideas that, as you probably know, that even ocean surface weathering, subsurface weathering is important to some degree, and that might have played a role very early in Earth's history. For example, in the Hadean, it's pretty clear that Earth did not have major continents exposed in the Hadean. Probably the planet was mostly an aquaplanet with very small exposed rock surfaces. And let's face it, we know that Earth had volatile cycling very early on. How it did that volatile cycling is still an unsolved problem in a sense, but it could, ocean weathering could have played a role in that.
We have a question from Pedro.
Hi there. Hi, Michael. Thank you very much for the excellent presentation. Have you looked at the seasonal cycle and the climate variability? I didn't see your time step from the climate simulations, but are you able to look at the seasonal cycles and the climate variability?
Absolutely. Yeah. I mean, one thing I didn't get into because it's just, I didn't want to talk for too long. I did show you some seasonal cycle things, like I showed you the growth of the ice sheets in those 50-year climatological means for the different seasons, right? So we can definitely look at things like that. It's just a question of how much, how much space you have in a blog and in a paper too, for that matter. But we can definitely see, seasonal cycle changes in the model very, very clearly. That's absolutely no problem at all.
And kinds like extremes or so, if you can have a kind of a similar global average, but you can have a lot of variability and some kind of the appearance of some extremes or so. You didn't look at that, no?
I didn't look at it anymore in the sense that I was looking at those ice sheets. So I looked at those climatologies, and I also looked at the temperatures in those climatologies. So I didn't see anything extreme, at least in those 50-year. And that's typically what I get all these ideas from the Earth side of the house. They like to use these 50-year climatological means at the different solstices. So that's what we did. But I didn't see anything extreme popping up in the models. But one thing I just want to mention, Pedro, and I'm so glad you brought this up, is that one thing that my group is very keen on is that we publish all of our NetCDF output from the model. So the summary files are all available. And if anybody ever wants the raw files, like every single month for 2,000 years, we can provide that. So that's something that we do. And we not only that, we also provide the model's open source. We provide all the boundary condition files. We provide all the setup files. We even run yearly tutorials for people how to use the model. So anybody can reproduce any simulation we make in any paper we write. So if you're interested and you really want to get into it,
thank you very much.
Yeah, I can give it to you, and it's no problem.
Thank you. Thank you very much.
Welcome.
We have Rodrigo now. Go ahead.
Hi, Michael. Thank you for your presentation. Before my questions, I would just like to add that I know almost zero about this topic, and so it will be a different kind of questions. Why did you often use the exoplanet expression, even though throughout your presentation you were always discussing about Earth? And the second question would be, if you could give some info on what drives this line of research.
Yeah, so it's exactly what you said in the first part of your question. What drives the line of research is that my group is not only interested in deep time climate for Earth, but we're very interested in Earth through time. We're interested in Mars through time. We're interested in Venus through time. And for us, moving forward in time is the same thing. So, we have more information about the worlds in our solar system than we're ever going to have about any exoplanet in our lifetimes, easily. Nobody's going to argue with that. So our idea is to validate the model, in a sense, in this whole suite of scenarios that we have for the worlds in our solar system. So that's why I always want to tie it back to the exoplanet studies in a sense, because what we're doing is we're providing the exoplanet community a view into how these planets are moving through time, what their climates are like, and what they can be like. So, for example, most people who do exoplanet climate modeling, what do? They model aquaplanets, or they take a modern Earth land sea mass and topography and they model that. And then what do? They might make decentricity 0, or they might make it, modern day Earth. That's it. That's about all they do. And for years, we've been trying to impress upon people that this is insufficient. And that, as you saw in these simulations, where the continents reside and what the topography is, what the topographic relief is, plays a key role in the climate. So I didn't go into it, but for example, in that Amazia simulation, you could see a situation where if the continents were even more packed farther north in a bit, and were a bit higher even, you could end up locking up most of your ocean in the poles, in the same way that it's all locked up on Mars. You have roughly 100 water global equivalent layer on Mars locked up in the polar caps. I'm not saying you're going to lock up all of Earth's water, but you could lock up a lot of it in the caps. And that's something people haven't thought about. They've only thought about it in terms of these very tidally locked worlds like M dwarfs, where people have made estimates that you could trap most of your water on the side that doesn't face the star. But here we have a situation where it's pretty obvious you could concoct a scenario where everything's trapped in the poles. Just lower the insulation by 20%. Take your Amazia simulation. Let's say this happened 4 billion years ago or 3 billion years ago. That's it, game over. You're all locked up here. You're going to have to wait till your sun gets warm to get out of this frozen state, in a sense. So that's why we're always tying it back, in a sense. But that was a really good question.
Thank you.
Welcome.
Thank you. Any further questions, João?
Yeah. So I think that's the what I find fascinating in this work is to think on the possibilities and to think. And I think another important thing is to look back to the past, right? Because we had these two supercontinents like Pangaea that looked very much like Orica, and maybe Rodinia that looked very much like the Amazia, and you had the snowball, right? So maybe that, but that links to what I wanted to ask you, or how we should go, is that maybe what took Earth out of the snowball was the geodynamics. So in this models are just making like really, it's drawings, right? That we are drawing for the position of the supercontinents. But I think that could be something that will worth investigate, and something that I think I would like to incentivize even in IDL, which is to actually have a lot of informed geodynamics, because as you say, the CO2 will vary a lot. And that will depend on the amount of ridges or subduction zones or things like that. So it will be nice to have, this new global geodynamic models with mantle convection and plate tectonics that could provide you a hint on, how will the atmosphere be or react to this kind of different geodynamics. So do you think there is a way to go in that direction? And especially, trying to link, maybe you could even, link with the work that these guys have been doing in ETH. They actually model the geodynamics of other Earths. So linking these geodynamics and climate models. Do you think that's something we should pursue?
Yeah. I think so. I mean, there's a lot of, maybe you're not aware of it, but there's been a lot of fights actually in the exoplanet modeling community by different groups. For example, trying to figure out what super Earths would be like. What are the geodynamics of super Earths? Some people said, oh, they're going to be exactly like Earth. It's no big deal. Everything scales linearly, blah, blah, blah. And other people were saying, no, you're crazy. That's not at all the same. There's all these chaotic processes involved, and things are completely different. So yeah, I completely agree, João. There's a huge role to be played here, because not only the the geodynamics of Earth changing through time and how it's moved forward in time, but also geochemistry. How does that change? Or just, I don't know if any of you saw it, but a paper just showed up, I guess it was an LPSC abstract, to be frank, it's not even a paper yet, where this graduate student and his team have this hypothesis that the LLSVPs, so these are these, I forget what it stands for, but they're connected to large igneous provinces. Maybe you know what it stands for.
Yeah, the low shear zones in the mantle.
Low shear wave.
Yes, you all know exactly. So his hypothesis is that those things sitting at the bottom of the mantle core boundary, I guess that's where they sit, are left over from the Theia impactor that created the moon.
Yeah.
And that's why we have those. So wouldn't that be, I mean, if it's right, wouldn't it be fascinating that we wouldn't have most of the mass extinction events in Earth's history? We wouldn't have large igneous provinces if it wasn't for the moon completely changing the geochemistry and the geodynamics of the planet early on. I don't know if that's right, but those are the kind of things that you all can play a huge role in helping us better understand. What are really the role of impactors and the geochemistry of these worlds? Is this why Venus and Earth are so different? Is it the geochemistry? We don't have any constraints per se for Venus's geochemistry. But if Venus was never hit by a Theia impactor, we don't know if it was or wasn't. But if it wasn't, does that play a role in its long-term geodynamics? Those are questions we don't know the answers to.
Shaking I think the Earth seems very much tuned to host life. That's crazy when you start to think on the things that you are dependent on, not just hosting, but being able to involve life, right?
Oh yeah, yeah. I mean, life's had 4 billion years to make its influence on this planet. I completely agree. It plays. I mean, it's playing a key role in the nitrogen cycle, as we know. It's playing roles in the carbon cycle. I mean, that's another thing that I think, at least on the exoplanet side of the house, we're only beginning to explore. And I think in paleoclimate, that's still an open area of research, right? What role did the methanogens play in early Earth history, for example?
Now, I always used to say that, like sometimes you think you're talking about exoplanets, but then, the where life could grow or appear in a different planet. And I never actually didn't thought about it until she mentioned is that don't forget that life appeared when the Earth was in the Archean. So it was not like today. We all think, oh, we need to have life, we need to have Earth like we have today. I said, no, for it to start, maybe you need to have something like the Archean, and then for it to evolve, you need to have something like Earth today, and that's not easy, as you're showing with the models.
Yeah, I mean, we have these, ancient stromatolites, these microbial mats sitting around from 3.5 billion years ago. It's remarkable. And certainly they played a role in the climate and the way the planet moved forward in time. There's no doubt. She's absolutely right. We should look at those things more closely.
Okay, I don't want to monopolize I miss these discussions. We need to gather in a Congress somewhere.
We'll get there eventually. Maybe it'll be a few more months, but let's hope so.
Okay.
Any further questions?
Do we have any students here? Because I can just say that I heard there's a group in IDL that is started by a student. I was one of the students and Ricardo told me there's a small group interested in investigating exoplanets.
Mm-hmm.
And I think that's something really that we should support, because I think, especially for students, it forces you to think out of our boundaries, and our boundaries being not Earth, but the solar system, think the possibilities. And that's something we may be able to actually, as you say, we're never going to be there or be able to understand its geodynamics at depth, but we may be in a era where we're going to have a lot of information from exoplanets, and that's incredible, really incredible. And other planets, you have all the probes on Mars now. Everybody is looking for.
Yeah, we didn't even talk about the ocean worlds, like the outer ocean worlds. What's going on there? There's going to be very interesting things going on in these subsurface oceans that we haven't even just starting to get into. But you're right, the parameter space is huge. And I think we need more geodynamics people thinking about these things. It's only beginning now. There's a few people at ETH that have thought about these things, and a few other places. But I think it's ripe for some very interesting science from your side of the house. You guys have a lot contribute, and the students especially, because you're the ones that are going to be there when these exoplanet discoveries start taking place in the coming decades, whereas people like me will be sitting at home smoking cigars and reading literature by the time that happens. So.
And they will have to be, I think they will have to be very creative, because as you say, it's very difficult to get information. So you have to know, so you can, I don't know, can you, maybe I'm very ignorant about it, but at this stage, you can only say a few things about the atmospheres of the exoplanets, right?
We can say almost nothing. We can say nothing, really. We haven't detected.
It just a dot passing through a.
Yeah, that's all it is. I mean, all we can say is that, you know, where the planet is in its orbit about the star, how much incident radiation is it receiving from the star? What does that radiation look like? Is it more peaked in the UV? Is it more peaked in the infrared? But we have not detected an atmosphere around a terrestrial exoplanet. We haven't done that. We've only detected some species in super Jupiter type planets around nearby stars. There's hope that JWST will be able, I'm sorry, I should be careful with acronyms. The James Webb Space Telescope, which is the Hubble Space Telescope's successor, which is going to be launched hopefully later this year. There's hope that it may be able to detect some carbon dioxide lines around terrestrial worlds, but it's not clear. I would say a lot of our modeling studies show it's going to be very, very hard for it to detect it. So I'm hoping that maybe with JWST, this space telescope that's going to go up, we might be able to see if they have CO2 dominated atmospheres. But for example, if they're N2 dominated with trace CO2 like our planet's atmosphere, you probably won't see very much. It'll be very hard to detect. We really need a new generation of space telescopes, and there are some plans to make some ground-based upgrades. Of course, the Europeans are building the ELT. We have these very original names for things, extremely large telescope, you know. So 40-meter class telescope. Not that the North Americans are any different. They also come up with silly names for things, but yeah, I mean, we're talking of probably, you know, in the next 5 to 10 years, we hope to be able to start detecting what these atmospheres around these planets look like. And, but, you know, detecting trace gas species is going to be very, very hard. I mean, we really want to detect, for example, ozone. That would be really great, but it's going to be very hard to find that. But again, you'll have a very big role to play. I mean, again, you know, what kind of, you know, if we can give you some geochemistry constraints, you know, because, for example, the star's chemical makeup are different in these nearby stellar systems with planets. And there's ideas around that. If the chemical makeup of the star is different, then the protoplanetary disk that the planets formed around could be different. So you have different kinds of metals, different volatile constraints. What does that go into your geodynamics model? You know, what if, you know, the silicate to carbon ratio is different by a factor of 2? How is that going to change your models? Will it change the models? Are your models, can they handle that? You know, I mean, these are all really important things that we need going forward. And again, even for our neighbors, like I said, for Venus, we really don't understand fundamentally why it's so different from Earth. So it's a quandary in a sense. It's going to be very surprising in a sense, maybe not too surprising now because we've shown that it's possible, but it will still be surprising if we find a planet like Venus at the same distance from its parent star and it looks like it has an atmosphere like present-day Earth. That would be really surprising, but not completely unexpected.
Okay, thank you, Michael. I think that's great. We can continue next time you visit us.
Definitely. Thank you all so much. I really appreciate your questions. Really enjoyed seeing you all, and good luck with your conference.
Thank you for, it's finishing now. You're the last person talking.
All right, well then.
You've just closed it perfectly.
Okay, enjoy your afternoon then. In that sense.
Yeah, thank you, Michael, for your very nice presentation. And thank you all for coming to the second annual conference of IDL. And thank you all the speakers and see you next time, okay? Thanks.
Thank you, bye.
Thank you. Bye.